The story begins in darkness, not the darkness we know, but a primordial absence where time and space themselves were still unformed. Imagine closing your eyes and feeling nothing, no before and no after, and then sensing a whisper of an impulse. In that whisper, a universe appears, in the smallest fraction of a heartbeat, more brief than any conscious thought. The cosmos blossoms from a point of infinite density and energy. The Planck time, when all forces are still one. Temperatures climb beyond imagination, and the fabric of reality vibrates with possibilities. It is as if the cosmos is taking its very first breath, and we are floating within that inhale, suspended in the glow of pure potential. After that initial breath, the universe begins to expand. It's difficult to convey how quick this was. In the time it takes for light to cross a proton, the universe races outward. All the forces we know remain unified, and in that unity there is no contrast, no distinction between what holds things together and what pushes them apart. We drift through this infant space, sensing only uniformity. Yet even here, there is the hint of change, because expansion dilutes the searing energy. It cools ever so slightly, and as it does, tiny fluctuations emerge, subtle ripples on a sea of fire. They are so small that only the cosmos itself can notice them, but they will become important later. As the first fraction of a second passes, gravity begins to peel away from the other forces. The symmetry shatters. Imagine the feeling of a sensation you cannot yet name suddenly becoming distinct. That is how the universe experienced the separation of gravity. Now there is a force that can pull matter towards itself, and a force that does something different. Within a heartbeat, the strong nuclear force follows, and the stage is set for matter to form. Every point of space is still unimaginably hot, but those initial ripples have grown just enough to seed the first variations in density. The cosmos is still an ocean of radiant particles, but the seeds of structure are being sown. The universe then undergoes a dramatic expansion called inflation. One can imagine a gently glowing sphere suddenly inflating to fill a room in a blink. Except the universe expands far more than 100 trillion times its size in a fraction of a second. This is a phase when a field that drove the expansion, a scalar field permeating all space, dominated the energy. During inflation, the quantum ripples that existed before are stretched beyond any horizon. They freeze as patterns on the expanding fabric, to be rediscovered later as the seeds of galaxies and of more exotic entities. The speed of this expansion is so extreme that any pre-existing structures are smoothed away. What remains is a nearly uniform, flat cosmos with an almost even glow. When inflation ends, the energy driving it is transferred into a hot bath of particles and radiation. This reheating floods the universe with quarks, leptons, and photons. At around 1/10 billionth of a second, the temperature is so high that quarks roam free, not yet confined into protons or neutrons. The universe is now dominated by radiation, a seething relativistic fluid that behaves in subtle ways. Imagine being immersed in a hot wind that moves near the speed of light. Pressure from this wind is strong enough to counter gravitational collapse on small scales, and any ripples of density must be large enough in extent or amplitude to overcome that pressure. Gravity and pressure engage in a delicate dance. The universe at this stage is like an ocean in which waves can travel very fast, because the speed of sound in a relativistic fluid is close to the speed of light, divided by the square root of 3. This means disturbances propagate swiftly, smoothing out variations that are too small. Only fluctuations larger than a characteristic scale, the analogue of the gene's length, have the chance to collapse under their own gravity. These early fluctuations are tiny in magnitude, but they are the seeds from which all later structure emerges. Each ripple is a potential site where matter might one day gather, or, if conditions are right, where a dense pocket may collapse to form something far more exotic than a galaxy. As the universe expands and cools further, the strong nuclear force binds quarks into protons and neutrons. This happens around a microsecond after the beginning. These newly formed hadrons still interact vigorously with the surrounding radiation. Neutrinos decouple, streaming freely through space and carrying away information about the earliest times. Moments later, electrons and positrons appear in abundance, only to annihilate in pairs, filling the cosmos with even more photons. Throughout these early epochs, the energy density remains dominated by radiation, and the cosmic soup continues to dilute and cool. Around a few minutes after the beginning, protons and neutrons begin to assemble into light nuclei. Hydrogen, helium, and trace amounts of lithium form through nuclear fusion. This primordial nucleosynthesis locks in the chemical composition that will persist for eons. The universe cools to about 1 billion degrees, still unimaginably hot by any human standard. Yet the processes unfolding are gentle and ordered. Each fusion reaction is a quiet handshake between particles that have only recently acquired their identities. These first atoms will be the building blocks of stars, planets, and eventually life itself. After nucleosynthesis, the universe enters a long epoch where radiation still dominates. During this era, lasting hundreds of thousands of years, photons scatter off free electrons and protons, making the cosmos opaque. We can picture an endless fog of light in which no photon can travel far without bumping into a charged particle. This photon epoch ensures that matter and radiation remain tightly coupled, oscillating together. Acoustic waves propagate through this plasma, leaving imprints that we will later observe as peaks in the cosmic microwave background. In this foggy sea, the seeds planted during inflation continue to evolve quietly, their amplitudes growing slowly under the influence of gravity. At about 300,000 years, the universe cools to a few thousand degrees, cool enough that electrons can combine with nuclei to form neutral atoms. This recombination causes photons to decouple. Suddenly, light can travel freely. The fog lifts, leaving behind a transparent cosmos bathed in a warm glow, the light that we now detect as the cosmic microwave background. The composition at this time is roughly 3/4 hydrogen and 1/4 helium, with a sprinkling of other elements. The densest regions of the primordial plasma begin to attract more matter, while the underdense regions become voids. Gravity gradually becomes the sculptor, carving out the cosmic web we see today. Even after recombination, the universe remains dark to human eyes for a long time. There are no stars yet. The first luminous objects will not ignite for hundreds of millions of years. These years are known as the cosmic dark ages. During this period, matter continues to collapse into overdense regions, seeded by the earlier fluctuations. Gas clouds grow denser, eventually forming the first stars and galaxies. But until that happens, the universe is filled mainly with neutral hydrogen and helium, cooled by expansion. It is in this serene darkness that the ripples imprinted by inflation and shaped by radiation gradually reveal themselves. The early universe was primed for extremes. Densities were extraordinary, temperatures were searing, and forces were unified. The conditions were so intense that pockets of space could, under the right circumstances, collapse into black holes without ever going through the life cycle of a star. These would be primordial black holes, remnants of processes occurring before the first stars ignited. They would bear witness to the physics of the earliest times and to the interplay of gravity and quantum fluctuations. To understand how such exotic objects might form, we need to explore how gravity and pressure work in this young universe, and how tiny ripples can grow into regions dense enough to collapse. Let us now turn our attention to gravity's role in the young cosmos. Gravity is a curvature of space-time. It guides the motion of matter and light, shaping the geometry of the universe. In the radiation-dominated era, pressure and energy density are intimately linked by a simple relation. The pressure is 1/3 of the energy density. This relation means that sound waves in the plasma travel at a significant fraction of the speed of light. When a disturbance forms, pressure tries to smooth it out, while gravity strives to make it collapse. The outcome depends on the wavelength and amplitude of the disturbance. It is a cosmic tug-of-war. The concept of the gene's length provides insight into this tug-of-war. In Newtonian terms, the gene's length is the scale at which gravity overwhelms pressure. For a relativistic fluid like the early universe, this scale is large because pressure support is strong and the speed at which information travels is high. Only perturbations larger than the gene's length are immune to the smoothing effect of pressure. Smaller perturbations oscillate as sound waves, never collapsing. Larger ones can overcome pressure and start to grow. In the young universe, therefore, only the largest ripples have a chance to become something more than gentle waves. To picture this, imagine a vast ocean with waves of many sizes. The smallest ripples are swiftly erased by the wind, but the largest swells roll on, unaffected by the surface breeze. In the cosmic ocean, the wind is the pressure of radiation, and the swells are density fluctuations. Over time, these swells can grow under their own gravity, but they need time, and the universe is expanding. Expansion dilutes matter and weakens gravity's grip. Thus, for a perturbation to collapse in the radiation-dominated era, it must be both large and sufficiently overdense. Otherwise, the expansion carries it away before gravity can do its work. Because the speed of sound is high, information travels quickly across the cosmos. When a region becomes slightly denser, pressure pushes outward, sending sound waves to its surroundings. These waves radiate energy away from the overdense region, reducing its density. At the same time, gravity pulls matter inward. The interplay of these two processes determines whether a perturbation will oscillate or collapse. In essence, the early universe is a resonant instrument, with modes of oscillation determined by its density, expansion rate, and composition. As the universe cools, the speed of sound gradually decreases, and the gene's length shrinks. Smaller perturbations that were once smoothed out become gravitationally unstable. These smaller seeds will eventually grow into galaxies and clusters. But the primordial fluctuations responsible for black hole formation need to be extreme even earlier. Only those that exceed a certain threshold density, contrast at the moment they enter the horizon, can collapse directly into black holes. Understanding how these thresholds arise requires a closer look at quantum fluctuations and the process of horizon crossing. During inflation, quantum fluctuations in the field driving the expansion are constantly being generated. They start as microscopic variations, like tiny ripples on an invisible surface. Inflation stretches these ripples to astronomical scales, freezing them outside the horizon, where they can no longer be affected by causal processes. These fluctuations become classical perturbations, imprinted on the geometry of spacetime. They are characterized by a nearly scale-invariant spectrum, meaning that fluctuations of different sizes have similar amplitudes. This pattern is a signature of the exponential expansion that occurred during inflation. Once inflation ends and the universe becomes radiation-dominated, these perturbations eventually re-enter the horizon. Until then, they are effectively frozen. But as the universe expands, the horizon grows. When a perturbation's wavelength becomes smaller than the horizon, causal physics can act on it. Perturbations with longer wavelengths remain frozen for longer periods. The time at which a perturbation re-enters the horizon is crucial. It determines the mass scale associated with that perturbation. This mass is roughly the amount of matter contained within the horizon at that time. The concept of a horizon mass helps translate the abstract notion of horizon crossing into concrete numbers. The horizon mass at a given time is approximately the mass of all the energy within a sphere whose radius is the particle horizon. In simple terms, the horizon mass is proportional to the cube of the horizon radius, which itself grows proportionally to the age of the universe. One finds that the horizon mass scales as the age divided by the gravitational constant times the cube of the speed of light. At the earliest times, this mass is tiny. At the Planck time, it is less than a gram. A fraction of a second later, it can be as much as thousands of solar masses. For example, at a time around 10 to 23 seconds, the horizon mass is roughly 1 billion tons, which sounds enormous, but is minuscule compared with astronomical objects. At 1 second, the horizon mass can reach up to 100,000 times the mass of our Sun. The mass of any black hole formed from a perturbation entering the horizon is expected to be some fraction of this horizon mass. This is because the region that collapses cannot be much larger than what fits inside the horizon at that moment. Otherwise, different parts of the region cannot communicate and collapse coherently. This link between horizon entry and black hole mass means that primordial black holes could span a vast range of sizes. Those forming at the very earliest moments would be tiny, perhaps microscopic by human standards, while those forming later could be as massive as stars, or even larger. The distribution of masses depends on the spectrum of primordial fluctuations and on how these fluctuations evolve. If certain scales are enhanced, perhaps by features in the inflationary potential, then black holes of particular masses could be produced in abundance. Otherwise, black holes might form only rarely, scattered across the early cosmos. But not every perturbation that enters the horizon collapses. The amplitude of the fluctuation matters. We describe the amplitude in terms of the fractional overdensity, denoted by delta. It is the difference between the local energy density and the background density, divided by the background density. When a fluctuation enters the horizon, if its delta is below a critical threshold, pressure forces and expansion will dominate, causing the perturbation to disperse or oscillate rather than collapse. Only if delta exceeds a critical value can gravity overcome pressure and drive collapse. The critical threshold for collapse in a radiation-dominated universe is surprisingly high. Simple arguments based on the equation of state suggest that delta needs to be at least 1/3. More detailed numerical simulations yield thresholds closer to about 45%. This means the overdensity must be almost half again as dense as the surrounding regions to collapse directly. Such large fluctuations are rare if the primordial perturbations follow a nearly Gaussian distribution. The probability of a given region exceeding the threshold drops rapidly as the threshold increases. Therefore, the abundance of primordial black holes is extremely sensitive to the amplitude of primordial fluctuations. If the fluctuations are too small, almost no regions will exceed the critical density contrast, and few or no black holes will form. If the fluctuations are slightly larger, the number of collapsing regions could increase dramatically. This sensitivity makes primordial black holes a unique probe of the physics of the early universe. They can amplify tiny differences in the initial conditions, leaving behind a cosmic fossil record of the inflationary epoch. To estimate how many primordial black holes might form, cosmologists often assume that the initial perturbations follow a Gaussian distribution. In this case, the fraction of horizon-sized regions that collapse into black holes depends on the root mean square amplitude of the perturbations and the critical threshold. The probability is given by the complementary error function, which falls off rapidly for large thresholds. Even a modest increase in the amplitude can change the abundance by many orders of magnitude. This is why primordial black holes could be incredibly rare or relatively abundant, depending on the details of the early universe. It is also possible that the fluctuations are not strictly Gaussian. Some theories of inflation predict localized enhancements or non-Gaussian features that could produce a higher abundance of black holes. In scenarios where the spectrum of perturbations has a bump at a particular scale, a narrow range of black hole masses may be produced in significant numbers. These models are attractive because they allow primordial black holes to contribute to dark matter without overproducing black holes at other masses. However, they also require fine-tuning of the inflationary dynamics, and observations of the cosmic microwave background and large-scale structure place strong constraints on such features. Beyond amplitude and distribution, the equation of state of the universe at the time of collapse also influences the threshold. During the radiation era, pressure is high, making collapse more difficult. If, however, there are epochs when the universe behaves differently, for instance, if the equation of state changes due to a phase transition, then the threshold may be lower. This would make it easier for fluctuations to collapse. Some models explore the possibility of a soft equation of state at very early times, which could lead to a larger abundance of black holes with specific masses. It is important to remember that primordial black holes are fundamentally different from black holes formed later in cosmic history. When we think of black holes, we often imagine the remnants of massive stars. These stellar black holes form when stars with more than about 8 times the mass of our Sun run out of nuclear fuel. The core collapses, and if sufficient mass remains, gravity compresses it beyond the point where light can escape. Stellar black holes typically have masses ranging from a few to a few tens of solar masses. They are often found in binary systems, where they accrete matter from a companion star and emit X-rays. Primordial black holes, in contrast, did not come from stars. They were born directly from the fabric of the early universe. In the first second after the Big Bang, pockets of space with sufficient density could have collapsed into black holes with masses spanning many orders of magnitude. Some could be as light as a fraction of a gram, others as heavy as thousands of suns. Because the conditions that allowed their formation ended as the universe expanded and cooled, primordial black holes would carry imprints of physics that cannot be reproduced elsewhere. They are time capsules from an era we can never visit. The range of possible masses for primordial black holes is staggering. At the low end, there could be black holes 100,000 times lighter than a paperclip. At the high end, there could be ones 100,000 times heavier than the Sun. This range is dictated by when in the cosmic timeline the corresponding fluctuations entered the horizon. Tiny mass black holes would have formed almost instantly after the Big Bang, while massive ones would have formed later, perhaps closer to the era of nucleosynthesis. The broad mass spectrum means that primordial black holes could, in principle, account for dark matter, seed galaxy formation, or remain hidden entirely. Many small primordial black holes would not have survived to the present day. According to quantum mechanics, black holes are not perfectly black. They emit radiation through a process known as Hawking radiation. This effect arises because the curvature of spacetime near the event horizon allows for particle-antiparticle pairs to be separated, with one particle escaping and the other falling in. The escaping particle carries away energy, causing the black hole to lose mass. The temperature of this radiation is inversely proportional to the black hole's mass. Larger black holes radiate more slowly and are colder. Smaller black holes radiate more quickly, and our hotter ones radiate more quickly and are hotter. For stellar mass black holes, the temperature of Hawking radiation is exceedingly low. A black hole with the mass of the Sun would have a temperature of about 100 nanokelvins, far colder than the cosmic microwave background. It would take a time vastly longer than the current age of the universe for such a black hole to evaporate. Even black holes with tens of solar masses radiate so little that evaporation is effectively irrelevant on cosmic timescales. This means that any primordial black holes heavier than the threshold of about 100 billion kilograms would still exist today, emitting only a trickle of radiation. However, for much lighter primordial black holes, Hawking radiation is significant. A black hole with a mass of around 100 billion kilograms has a temperature on the order of 1 trillion degrees and would emit intense radiation. Such a black hole would complete its evaporation within the age of the universe. Smaller black holes would have evaporated even faster. The final stages of evaporation would produce a burst of high-energy particles and gamma rays. If such events occurred nearby, they would be detectable as brief flashes, but they would be rare and short-lived. Thus, any primordial black holes below this mass threshold are unlikely to be present today. The life cycle of a primordial black hole is therefore governed by a cosmic clock set by Hawking radiation. Tiny black holes evaporate quickly, leaving behind nothing but a burst of energy. Intermediate mass primordial black holes may still be around, but they would be small and emit more radiation than their heavier counterparts. Those above a certain mass would be effectively eternal on current cosmic timescales. Their presence or absence provides clues to the conditions of the early universe and to the validity of theories beyond the standard model. As the universe evolves and structures form, primordial black holes, if they exist, could influence the growth of galaxies and clusters. Black holes of a few to several tens of solar masses could merge with one another, or with other black holes. Such mergers produce gravitational waves, ripples in spacetime that propagate outward. Observatories have detected mergers of black holes in this mass range, sparking interest in the possibility that some of these objects might be primordial. Determining whether a given merger originates from stellar remnants or primordial black holes is challenging but not impossible. It depends on factors like the distribution of masses, spins, and environments. Primordial black holes could also contribute to dark matter. Dark matter is an unknown form of matter that makes up most of the mass in the universe. It does not interact with light, but its gravitational effects are evident in the motions of galaxies and the cosmic web. If primordial black holes exist in sufficient abundance, they could account for some or all of dark matter. Observational constraints, however, limit the allowed mass ranges. For some mass ranges, primordial black holes cannot be abundant because they would disrupt observations of gravitational lensing or cosmic microwave background anisotropies. For other mass ranges, they remain plausible candidates. The distinction between primordial and stellar black holes is thus not just about origin, but also about the clues they offer. Stellar black holes tell us about stellar evolution, nuclear physics, and the dynamics of galaxies. Primordial black holes, if observed, would reveal information about the earliest fractions of a second in cosmic history, the nature of inflation, and perhaps the properties of high-energy physics beyond the reach of terrestrial experiments. They bridge astrophysics and particle physics, connecting the macroscopic with the microscopic in a way few phenomena do. To summarize, the early universe provided a unique laboratory where gravity and quantum mechanics cooperated to create extreme conditions. Tiny quantum fluctuations were stretched by inflation to cosmic scales, seeding both galaxies and, in rare cases, the collapse of black holes. The interplay of pressure and gravity in the radiation-dominated era set stringent thresholds for collapse, meaning only exceptional overdensities could form primordial black holes. The mass of these black holes was tied to the horizon mass at the time of horizon entry, leading to a wide spectrum of possible masses. Their lifetimes were governed by Hawking radiation, with only those above a critical mass surviving to the present day. As we drift through this tale, we recognize that our journey is far from over. We have touched upon the birth of the universe, the emergence of gravity, the whisper of quantum fluctuations, and the delicate conditions required for primordial black holes to form. We have distinguished these ancient ghosts from the black holes born of dying stars, and glimpsed the role of Hawking radiation in their demise. Yet there is much more to explore. Beyond this calm shore lies the deeper ocean of implications, how these primordial relics may have influenced the formation of galaxies, how they could be detected, and what they might tell us about the ultimate nature of reality. We will continue this exploration, gently, with curiosity and wonder, as the story unfolds. As we linger in the aftermath of recombination, let us dwell on the subtle details of that first light. The cosmic microwave background is more than a relic. It is a portrait of the infant universe frozen in time. Minute variations in its temperature correspond to the density fluctuations we have discussed. These fluctuations are tiny, 1 part in 100,000, yet they map the seeds of all structure. Imagine standing before a fogged window and noticing that the mist is not uniform. Some areas are slightly thicker, others thinner. From these almost imperceptible differences, the patterns of galaxies emerge. The microwave background reminds us that the cosmos has memory, and that memory is written in the faintest contrasts. The physics behind the cosmic microwave background teaches us about the curvature of the universe and its composition. By measuring the angular scale of the first acoustic peak in the temperature power spectrum, cosmologists determine that space is very nearly flat. Flatness implies a balance between the energy density and the critical density, a balance set by inflation. The heights and positions of subsequent peaks reveal the ratio of baryonic matter to dark matter, and the fraction of ordinary matter to radiation at the time of recombination. In this way, a map of ancient light allows us to deduce the contents of the universe. It is as if, by listening to a song, we can infer the size of the orchestra and the nature of its instruments. Further along in cosmic history, after the Dark Ages, the first stars switch on. These stars are massive and short-lived, comprised almost entirely of hydrogen and helium. Their ultraviolet radiation rayonizes the surrounding medium, ending the neutral state of the universe. This epoch of rayonization marks the end of the Dark Ages and the start of the universe we know. The process is patchy. Bubbles of ionized gas expand around clusters of early stars, eventually overlapping. Observing this era is challenging, but measurements of the cosmic microwave background polarization and radio observations of hydrogen lines offer glimpses. The first stars not only light up the cosmos, they also fuse the first heavier elements, seeding the interstellar medium with carbon, oxygen, and nitrogen. Galaxies form when gas falls into the gravitational wells created by dark matter halos. The dark matter collapses first because it interacts only through gravity and does not dissipate energy through radiation. Once halos form, gas can cool and settle into disks, forming stars. The structure of galaxies is thus intimately linked to the distribution of dark matter. If primordial black holes make up a significant fraction of dark matter, they would alter this distribution. They could also act as seeds around which gas accumulates, potentially aiding the formation of supermassive black holes at the centers of galaxies. The interplay between baryonic matter, dark matter, and primordial black holes offers a rich arena for theoretical exploration. Let us return for a moment to the quantum fluctuations that seeded these structures. The Heisenberg uncertainty principle tells us that the energy of the vacuum cannot be exactly zero. Even in the absence of particles, fields fluctuate. During inflation, these fluctuations become stretched to macroscopic scales. The gauge invariant curvature perturbation captures these variations in the fabric of spacetime. It is remarkable that quantum processes on subatomic scales can lead to galaxies spanning hundreds of thousands of light-years. This connection between the smallest and largest scales is one of the profound lessons of cosmology, weaving quantum mechanics and general relativity into a single narrative. The nearly scale-invariant nature of the primordial power spectrum means that fluctuations of different sizes have similar amplitudes. However, there is a slight tilt. Observations show that the spectral index is slightly less than unity. This tilt arises naturally in many inflationary models, reflecting the slow roll of the inflaton field down its potential. Small deviations from perfect scale invariance contain clues about the shape of the potential and the dynamics of inflation. Measurements by satellites, such as the Wilkinson microwave anisotropy probe and the Planck mission, have constrained these parameters with high precision, providing a window into physics at energies far beyond those accessible in laboratories. When perturbations re-enter the horizon during the radiation or matter-dominated eras, they evolve differently depending on the cosmic environment. In the radiation era, perturbations oscillate as acoustic waves due to the coupling between photons and baryons. Their growth is inhibited by pressure. In the matter-dominated era, after the universe has cooled enough that matter outweighs radiation, perturbations grow more efficiently because there is less pressure to counteract gravity. This change in the growth rate leaves imprints on the matter power spectrum. It also impacts the formation rate of primordial black holes, as the thresholds for collapse depend on the equation of state. The concept of the particle horizon deserves further contemplation. At any given moment, the horizon defines the maximum distance from which light could have traveled to an observer since the beginning of the universe. In the early universe, this distance is tiny, and the horizon grows with time. Regions separated by more than the horizon cannot influence each other because light has not had time to travel between them. During inflation, the horizon shrinks relative to the rapid expansion, causing regions that were once in causal contact to become causally disconnected. This solves the horizon problem. The observed uniformity of the cosmic microwave background across vast distances is explained by the fact that those regions were connected before inflation stretched them apart. There is also an event horizon in cosmology, distinct from the particle horizon. The event horizon is the boundary beyond which events can never be observed in the future, even if the universe exists forever. In a decelerating universe with no dark energy, the particle horizon and event horizon coincide. In an accelerating universe, as ours appears to be due to dark energy, the event horizon is finite. This means there are regions of the universe from which light emitted now will never reach us. These cosmic horizons remind us that there are limits to what we can know. Some regions and events lie forever beyond our observational reach. To appreciate the diversity of possible primordial black hole masses, consider the time dependence more precisely. A fluctuation entering the horizon at t equals 1 microsecond would correspond to a mass roughly equal to the mass of Earth. At t equals 1 second, the mass corresponds to roughly 100,000 solar masses. Between these extremes lie countless possibilities. A fluctuation entering at 1,000th of a second could produce a black hole of about a solar mass, while one entering at 1,000,000th of a second might yield a black hole with the mass of the Moon. Each mass corresponds to a specific epoch, linking black hole size directly to the age of the universe when it formed. This time-dependent horizon mass implies that processes occurring at different phases of the early universe can lead to distinct populations of primordial black holes. If a phase transition occurs, such as the QCD confinement of quarks into hadrons, it might temporarily change the equation of state and the speed of sound. Such changes could alter the threshold for collapse and enhance the formation of black holes of certain masses. Similarly, if inflation ends in a way that produces a spike in the power spectrum at a given scale, it could lead to a burst of black holes, all with similar masses. These features would leave signatures in the distribution of primordial black hole masses. The collapse process itself is complex. When a region of space becomes overdense, it initially expands along with the universe, then reaches a maximum size and begins to contract. If the contraction proceeds far enough and is not halted by pressure, the region can form an apparent horizon. Relativistic effects and pressure gradients shape this collapse. Numerical simulations show that the resulting black hole mass depends not only on the horizon mass, but also on how much the actual overdensity exceeds the critical threshold. Near the threshold, the mass scales as a power of delta minus delta sub c, reflecting critical phenomena in gravitational collapse. Thus, even small differences in the initial overdensity can lead to different final masses. Another important question is whether primordial black holes could form with significant rotation. Angular momentum in the early universe arises from vector perturbations, which are typically suppressed, so one might expect primordial black holes to be nearly non-rotating. However, if perturbations are not perfectly spherical, some angular momentum is inevitable. Rotation would alter the collapse and could lead to torus-like structures, or even fission, before a horizon forms. The spin distribution of primordial black holes is therefore a probe of the initial conditions. Observations of gravitational waves from merging black holes may one day reveal whether low-mass black holes are spinning, offering hints about their origin. Let us now expand on the distinction between stellar, intermediate, and supermassive black holes. Stellar black holes arise from the collapse of massive stars. When nuclear fuel is exhausted, pressure support disappears, and the core implodes. If the mass of the core exceeds the Tolman-Oppenheimer-Volkoff limit, no force can halt collapse. These black holes typically have masses from about 3 to a few dozen solar masses. They can be detected indirectly through their gravitational influence on companion stars, by observing X-rays from accretion disks, or through gravitational waves when they merge. Intermediate mass black holes occupy the range between 100 and 100,000 solar masses. Their formation is less well understood. They may result from the runaway collision of stars in dense clusters, or from the merger of stellar black holes. Evidence for such black holes comes from observations of ultraluminous X-ray sources and gravitational wave detections. Supermassive black holes, with masses millions to billions of times that of the Sun, reside at the centers of galaxies. They are thought to form through the accretion of gas, the merger of smaller black holes, or the direct collapse of massive gas clouds. Primordial black holes could provide seeds for both intermediate and supermassive black holes, offering a head start in the growth process. In discussing stellar black holes, it is instructive to follow the life of a massive star. Born in a molecular cloud, the star shines by fusing hydrogen into helium. When hydrogen runs out, helium fuses into heavier elements, and so on until iron is produced. Iron cannot release energy through fusion, and the core becomes unstable. Gravity wins, and the star collapses. If the core mass is above a critical value, it becomes a neutron star or a black hole. The outer layers are ejected in a supernova. This violent death enriches the interstellar medium with heavy elements. The remnant black hole retains the angular momentum of the star, often spinning rapidly. It may continue to grow if it has a companion or if it resides in a dense environment. The accretion of matter onto black holes is a luminous process. As gas spirals inward, it heats up and radiates, often producing X-rays. This radiation allows astronomers to infer the presence of unseen massive objects. In the case of supermassive black holes at galactic centers, accretion can power quasars and active galactic nuclei, emitting more light than entire galaxies. Observing these phenomena tells us about the growth of black holes over cosmic time. The correlation between the mass of a supermassive black hole and the velocity dispersion of its host galaxy's stars hints at a co-evolutionary relationship. If primordial black holes served as seeds, they might influence this relationship. The detection of gravitational waves has opened a new window into black holes. When two black holes spiral toward one another and merge, they emit gravitational waves carrying information about their masses and spins. The LIGO and Virgo observatories have detected several such events. Some of the merging black holes have masses around 30 solar masses, which is higher than typical stellar black holes in X-ray binaries. This has led to speculation that they may be primordial. By analyzing the distribution of masses, spins, and redshifts of these events, scientists hope to distinguish between primordial and stellar origins. If a population of low-spin, high-mass black holes is discovered, it could point toward a primordial origin. Now let us explore the quantum phenomenon of Hawking radiation in greater depth. Stephen Hawking showed that when quantum fields are considered in the curved spacetime around a black hole, particle-antiparticle pairs near the horizon can be separated. One particle falls into the black hole, carrying negative energy relative to infinity, while the other escapes to infinity as radiation. The black hole loses mass equal to the energy carried away. This radiation has a thermal spectrum with a temperature inversely proportional to the black hole's mass. The process is inevitable in quantum theory, and means that black holes are not eternal in a strictly classical sense. Black hole evaporation through Hawking radiation follows a simple relation. The power emitted is inversely proportional to the square of the mass. Consequently, the rate of mass loss accelerates as the black hole becomes lighter. For a black hole with the mass of Mount Everest, the temperature is about 100 million Kelvin, and it would evaporate in a timescale much longer than the age of the universe. For a black hole with the mass of a mountain, the temperature is even higher, and the evaporation time shorter. In the final moments of evaporation, the black hole would release a burst of high-energy particles and radiation. Detecting such bursts would provide strong evidence for the existence of primordial black holes. The search for evaporating black holes has motivated observations in gamma rays. Space-based observatories, like the Fermi Gamma Ray Space Telescope and ground-based Cherenkov telescopes, look for brief, intense flashes of gamma rays that could signal the final evaporation of a primordial black hole. Thus far, no unambiguous detections have been made, placing limits on the number of such black holes in the universe. These searches complement other constraints on primordial black holes, such as microlensing surveys that can detect the gravitational influence of compact objects on background stars. Gravitational microlensing occurs when a compact object passes in front of a distant star, bending and magnifying its light. The duration and amplitude of the magnification depend on the mass of the lensing object. Surveys of millions of stars in the Milky Way and in nearby galaxies have searched for lensing events caused by primordial black holes. The absence of a large number of microlensing events rules out primordial black holes as the dominant dark matter component in certain mass ranges. However, microlensing remains a powerful tool for discovering isolated black holes, whether primordial or stellar in origin. Another observational probe comes from the cosmic microwave background. If primordial black holes existed in significant numbers at the time of recombination, their gravitational influence would affect the distribution of matter and radiation. They could cause early matter accretion, heating the plasma and altering the ionization history. This would leave imprints on the temperature and polarization anisotropy spectra. Measurements of these spectra by Planck and other missions have been used to set limits on the abundance of primordial black holes. The constraints depend on the mass and on how efficiently the black holes accrete matter and release energy. Primordial black holes could also interact with compact objects such as neutron stars and white dwarfs. If a primordial black hole were to pass through a neutron star, it might trigger collapse by seeding and instability. Alternatively, if it became trapped in a neutron star, it could gradually consume the star from within. Such interactions could alter the population of neutron stars and lead to observable events like kilonovae. While these scenarios are speculative, they illustrate the diverse astrophysical consequences that could arise from a population of primordial black holes. The possibility that primordial black holes contribute to dark matter has sparked interest, because dark matter remains one of the great mysteries of modern physics. The leading candidate in many models is a new, weakly interacting particle, but decades of experiments have yet to detect such particles directly. Primordial black holes offer an alternative: compact, non-baryonic objects that interact gravitationally. If they exist in the right mass range and abundance, they could account for a fraction of dark matter. The challenge is to reconcile this with the many observational constraints across different scales and epochs. It is worth reflecting on the richness of the early universe's physics. The interplay of quantum mechanics, general relativity, and thermodynamics gave rise to phenomena that shape the cosmos to this day. The uncertainty principle seeded fluctuations, inflation stretched them, gravitational instability amplified them, and quantum field theory allowed black holes to evaporate. Each piece fits together in a mosaic that tells a story about beginnings. Our understanding of this story is incomplete, and primordial black holes represent one of its more enigmatic chapters. They remind us that there may be relics from the earliest times still hiding in the vastness of space. As we contemplate the potential existence of primordial black holes, we can't help but wonder about their environments. Where would they reside today, depending on their masses and the distribution of dark matter? They might be sprinkled throughout galactic halos, occasionally wandering through planetary systems. If a small primordial black hole were to pass through the solar system, it might reveal itself through subtle gravitational perturbations. Yet the vast emptiness of space makes such encounters extremely rare. Nevertheless, the thought that ancient black holes could be passing silently through the darkness adds an element of mystery to the night sky. In exploring these ancient relics, we also encounter deep questions about information. Hawking radiation leads to the black hole information paradox. If black holes evaporate completely, what happens to the information about the matter that fell into them? Does it disappear, violating the principles of quantum mechanics, or is it somehow encoded in the radiation? This paradox has spurred vigorous debate and research. Studying primordial black holes and their evaporation could provide insight into how gravity and quantum mechanics reconcile, perhaps pointing toward a theory of quantum gravity. Looking further ahead, one might ask whether primordial black holes could play a role in the far future of the universe. As ordinary stars burn out and galaxies evolve, black holes will persist. Given enough time, stellar and primordial black holes will evaporate through Hawking radiation, though this process will take unimaginable durations for large masses. Eventually, all black holes will evaporate, leaving behind a dilute sea of radiation. In this distant future, the universe will be cold and dark, save for occasional bursts from the final stages of black hole evaporation. Primordial black holes formed in the first instant may thus still influence the cosmos in its last. The prospect of detecting primordial black holes also motivates improvements in observational capabilities. Future gravitational wave detectors, such as LISA and the Einstein telescope, will observe lower frequencies, probing mergers of lighter black holes, and perhaps capturing signals from primordial black hole binaries. Next-generation gamma-ray telescopes and all-sky monitors will be more sensitive to short bursts, enhancing the chances of detecting evaporating black holes. Advances in microlensing surveys will monitor more stars with greater precision, further constraining or discovering compact objects. Each observational frontier brings us closer to answering whether primordial black holes exist. At the heart of this exploration is a philosophical reflection on the nature of beginnings. The early universe was a crucible where the laws of physics we know were forged, and where new physics might have operated. Primordial black holes, if they exist, are whispers from that crucible. Their formation required a delicate balance of forces and a set of conditions that may never occur again. They represent a bridge between the quantum foam and cosmic structure, between the Planck epoch and the present. They invite us to contemplate the unity of physical laws across scales and times. In meditating on primordial black holes, we also acknowledge the limits of our knowledge. Much of what we have discussed rests on theoretical frameworks and indirect observations. While we have compelling reasons to believe that quantum fluctuations seeded the cosmos and that Hawking radiation exists, we have yet to observe these phenomena directly in the context of primordial black holes. Our understanding remains provisional, awaiting the light of discovery. This uncertainty is not a weakness, but a source of curiosity and wonder. It is the open space in which imagination and inquiry thrive. As we prepare to transition to the next part of our journey, consider how the themes we have explored resonate beyond physics. The notion that something so small and fleeting as a quantum fluctuation can shape the destiny of galaxies mirrors how small choices in our lives can have far-reaching consequences. The idea that extreme conditions can give birth to new structures suggests that moments of chaos can lead to unexpected order. The story of primordial black holes thus offers not just scientific insight, but also a metaphor for transformation. As we venture onward, our thoughts turn to the invisible seas that permeate the cosmos. Beyond the light of the cosmic microwave background, there exist backgrounds of neutrinos and gravitational waves that carry whispers from the earliest times. The cosmic neutrino background decoupled when the universe was about a second old. We cannot see these neutrinos directly, but their presence influences how the universe expands and leaves subtle imprints on the pattern of anisotropies in the microwave background. They are ghostly messengers from the first moments, still streaming freely through space. In addition to neutrinos, there is a predicted background of primordial gravitational waves. Processes like inflation can generate a spectrum of gravitational waves that fills space with a faint hum. Phase transitions, cosmic strings, and the formation of primordial black holes themselves can also contribute to a stochastic gravitational wave background. Detecting this background would offer a new way to study the early universe, allowing us to listen to events that occurred when the cosmos was opaque to light. Future space-based interferometers may be sensitive enough to pick up these signals. The collapse of an overdensity into a primordial black hole is not a silent affair. Numerical simulations suggest that the dynamics of the fluid and the ring down of the newly formed horizon can produce bursts of gravitational radiation. These bursts would be faint, but collectively they could contribute to the gravitational wave background. Thus, the very act of creating a primordial black hole leaves a signature that propagates across the universe and endures to the present. Alternative formation scenarios broaden the range of possibilities. In some theories, the universe contains topological defects, such as cosmic strings or domain walls, remnants of symmetry-breaking phase transitions. Cosmic strings are like thin threads of concentrated energy stretching across space. When they intersect or form loops, they can radiate energy and sometimes collapse into black holes. Domain walls are two-dimensional surfaces separating regions of different vacuum states. Under certain conditions, their collapse can also produce black holes. Each mechanism yields a characteristic mass spectrum and abundance. Another intriguing possibility involves bubble collisions. During a phase transition, the universe might have nucleated bubbles of a new vacuum. When these bubbles expanded and collided, the energy released could have been sufficient to form black holes. The distribution of bubble sizes and the timing of collisions would determine the masses of the resulting black holes. These scenarios highlight how the details of particle physics models can influence the population of primordial black holes. Beyond their formation, primordial black holes may affect nucleosynthesis. As they evaporate via Hawking radiation, they emit a spectrum of particles that includes quarks and gluons. These particles hadronize into mesons and baryons, some of which may fuse into heavy nuclei. Researchers have proposed that evaporation could contribute to the abundance of certain heavy elements, particularly in the R process, which requires rapid neutron capture. Though uncertainties remain, the idea illustrates how primordial black holes could act as tiny furnaces, altering cosmic chemistry. The interplay between early universe physics and fundamental forces also manifests in baryogenesis, the process that generated the matter-antimatter asymmetry. Some models link baryogenesis to the same conditions that produce primordial black holes, suggesting that the collapse of fluctuations and the violation of certain symmetries may have occurred together. If primordial black holes are observed, their properties might therefore provide hints about why the universe contains more matter than antimatter. There are even connections to dark energy and modified gravity. The accelerated expansion of the universe today is often attributed to a cosmological constant or a dynamic field. Certain theories propose that black holes can interact with this field, accreting dark energy and changing their growth rates. If primordial black holes exist, they could serve as laboratories for studying such interactions. Observational signatures might include deviations in the distribution of black hole masses at late times. Quantum gravity offers another rich context. The structure of space and time near a black hole's horizon remains one of the greatest puzzles in theoretical physics. Competing approaches, such as string theory and loop quantum gravity, propose different microphysical descriptions of black hole entropy. Primordial black holes, with their range of masses, provide a setting where these ideas might be tested. The details of their evaporation could reveal whether information is preserved, whether remnants remain, or whether new physics emerges. In some speculative scenarios, black holes do not fully evaporate, but leave behind stable remnants. These remnants would be tiny, perhaps with masses near the Planck scale, but they could be abundant if many primordial black holes formed and evaporated early on. Such remnants would interact gravitationally and could contribute to dark matter. The possibility of remnants underscores how our ignorance of the quantum endpoint of black holes feeds into cosmological questions. The practical implications of tiny black holes extend even into the realm of imagination. Science fiction has long toyed with the idea of harnessing a small, artificially created black hole as an energy source. Hawking radiation from such a black hole could provide a steady output of high-energy particles. While far beyond current technology, this speculation reflects how understanding extreme physics may inspire visions of future innovation. Returning to observation, gravitational lensing remains a powerful probe. A primordial black hole passing in front of a distant star can act as a lens, temporarily magnifying the star's light. Surveys like OGLE, MACHO, and more recently OGLE4 and Gaia have monitored millions of stars for such microlensing events. So far, the data constrain the abundance of compact objects in various mass ranges, ruling out primordial black holes as the dominant form of dark matter in those ranges. Future surveys will extend these constraints to smaller masses. Other astrophysical phenomena also impose limits. The distribution of wide binaries, the stability of neutron stars, and the cosmic microwave background's anisotropy can be affected by primordial black holes. For example, if too many black holes of a certain mass existed, their gravitational interactions would disrupt binary star systems. Observations show that wide binaries are abundant, placing limits on the abundance of massive compact objects. Similarly, black holes passing through neutron stars could trigger collapse, and the absence of such collapses places further constraints. Gamma-ray observations provide yet another avenue. Evaporating black holes would produce high-energy photons, and instruments like the Fermi Large Area Telescope search for short, intense bursts. Although no definitive evaporation events have been recorded, the absence of detections allows astronomers to set upper limits on the number of low-mass black holes in the local universe. As instruments become more sensitive, they may either detect such events or tighten the constraints. On the theoretical front, the mass spectrum of primordial black holes can be more complex than a simple power law. Critical collapse produces a mass distribution that depends sensitively on how close the initial density contrast is to the threshold. Small differences in delta near delta sub C result in a range of final masses. Additionally, features in the primordial power spectrum, such as peaks or dips at certain scales, can imprint corresponding features in the mass distribution. Thus, Measuring the masses of primordial black holes could, in principle, probe the shape of the primordial spectrum. Some research explores the possibility of forming primordial black holes during epochs later than the radiation era. During matter domination, pressure support is negligible, making it easier for overdensities to collapse. If, for instance, a period of matter domination occurred during reheating, enhanced collapse could produce additional black holes. Likewise, scalar fields oscillating in a matter-like way can temporarily dominate the energy density, affecting collapse conditions. Each scenario broadens the range of masses and times at which primordial black holes might form. The interplay between black holes and cosmic structure formation is nuanced. Primordial black holes could act as seeds for larger structures by attracting surrounding matter. Alternatively, their gravitational potential could disrupt baryon acoustic oscillations or affect the formation of the first stars. The details depend on their mass and abundance, and ongoing simulations strive to capture these subtleties. Understanding these effects is crucial for interpreting cosmological surveys. Even the distribution of planets could, in principle, be influenced by primordial black holes. A black hole passing through a protoplanetary disk would gravitationally perturb the material, potentially triggering planet formation or causing instabilities. While such encounters would be rare, they are a reminder that primordial black holes, if they exist, are part of the cosmic environment that shaped everything from galaxies to planetary systems. As we dwell on these possibilities, our narrative returns to a contemplative tone. Imagine floating in intergalactic space, far from any star, aware that countless tiny black holes may drift unseen. Each one is a fossil from the universe's first moments. They are silent, cold, and dark, yet they carry within them the memory of extreme conditions when spacetime itself shuddered. Their presence adds depth to the cosmos, like hidden notes in a symphony. In this meditative state, consider the interplay between knowledge and mystery. We have used mathematics and observation to uncover much about the early universe, yet primordial black holes remain elusive. This elusiveness invites humility. The cosmos is vast, and our ability to probe it is limited. The unknown is not a void, but a landscape filled with potential discoveries. It beckons us to continue exploring with patience and curiosity. The narrative of primordial black holes is thus both scientific and poetic. It weaves together facts about density, contrasts, and Hawking radiation with imagery of waves and horizons. It invites us to slow down, to listen to the quiet stories encoded in the fabric of the universe. As we transition into the next phase of our exploration, hold on to this sense of wonder. The path ahead remains rich with questions, and each question is an invitation to deeper understanding. The cosmic microwave background not only provides a snapshot of the universe when it became transparent, it also serves as a canvas on which other processes paint subtle signatures. Primordial black holes can distort this canvas in several ways. If abundant, they would accrete surrounding matter and emit radiation that could slightly heat the primordial plasma. Such heating would leave faint deviations from the perfect blackbody spectrum, known as spectral distortions. Measurements by instruments like COBE and Planck constrain these distortions, thereby limiting the density of black holes in certain mass ranges. In the realm of gravitational waves, pulsar timing arrays offer a unique method. Millisecond pulsars act as precise clocks. Gravitational waves passing between Earth and the pulsar can cause tiny variations in the arrival times of pulses. A population of primordial black holes merging across cosmic time would contribute to a background of low-frequency gravitational waves. The North American Nanohertz Observatory for gravitational waves, and similar collaborations are steadily improving sensitivity, edging closer to the level where such a background might be detected. Accretion onto primordial black holes is another key process. In the early universe, gas was more uniform and dense than today, providing material that black holes could capture. Radiation from this accretion could ionize hydrogen and helium, contributing to the epoch of rhionization. However, observations of the timing and progress of rhionization constrain how much additional ionizing radiation could have been present. As a result, there are limits on how many primordial black holes can exist without disrupting the observed history of rhionization. Observations of the 21 centimeter line, produced by the hyperfine transition of neutral hydrogen, open yet another window. During the cosmic dawn, when the first stars and black holes formed, the 21 centimeter signal is sensitive to the temperature and ionization state of the intergalactic medium. Primordial black holes could heat or ionize the gas through accretion or evaporation, altering the 21 centimeter brightness temperature. Upcoming radio telescopes like the Square Kilometre Array will map this signal across cosmic history, providing new constraints on any exotic heating sources. The shape of the primordial power spectrum plays a crucial role in determining the abundance and masses of primordial black holes. Inflationary models can produce features such as bumps or dips in the spectrum if the inflaton potential has plateaus, kinks, or multiple fields. A localized enhancement in power at a certain scale translates into a higher probability of large overdensities, leading to a spike in the primordial black hole mass function. Thus, by studying the mass distribution, one might infer details about the potential that drove inflation itself. One of the most compelling connections involves supermassive black holes at the centers of galaxies. Observations reveal that nearly every massive galaxy hosts a central black hole with a mass millions or billions of times that of the Sun. How such giants grew so quickly after the Big Bang remains an open question. Primordial black holes with intermediate masses could have served as seeds, accreting gas and merging to build up the observed supermassive black holes. This idea links events in the first second to structures billions of years later. To unravel the mysteries of primordial black holes, scientists leverage multiple observational channels. Gravitational lensing monitors stars and quasars. Gravitational wave detectors listen for mergers. Gamma-ray telescopes watch for bursts. And cosmological surveys measure the cosmic microwave background and the distribution of galaxies. By combining information from these sources, researchers can cross-check signals and build a coherent picture. The interplay of diverse data sets enhances the sensitivity to subtle effects and reduces the chances of mistaking noise for signal. The microcosm of a quantum fluctuation and the macrocosm of a galaxy are connected through a chain of processes spanning dozens of orders of magnitude in scale. A fluctuation stretched to astronomical size by inflation can collapse into a black hole with a mass comparable to that of a mountain or a star. That black hole may then influence the formation of galaxies, which in turn host billions of stars, including those that may support life. In this way, the smallest seeds can influence the largest structures, reflecting a unity of scale in the universe. Humanity has long told creation stories that involve darkness and light, chaos and order. In many myths, the world arises from a primeval void or a cosmic egg. Modern cosmology echoes these themes in its description of a universe born from a hot, dense state, filled with quantum fluctuations. Primordial black holes could be seen as the shadowy remnants of this cosmic creation, formed when regions of the early universe briefly succumbed to gravity. The narrative is both ancient and new, blending scientific insight with enduring motifs. The metaphors of oceans and islands provide another way to imagine these ideas. Think of spacetime as a vast ocean, its surface rippling with waves of energy and matter. In some places, waves build upon each other, rising higher until they crest and break, forming isolated islands. Each island is a black hole, a region set apart from the rest of the sea. The horizon of the black hole is like the shoreline, a boundary where the rules of the ocean change. Beyond it, the currents of time and space flow inward and vanish. Contemplating life in the vicinity of a black hole prompts further imagination, while the environment near a stellar or supermassive black hole would be hostile to life as we know it. The physics of tidal forces, time dilation, and high radiation creates a landscape that challenges intuition. For a sufficiently large black hole, tidal forces at the horizon could be gentle, and time would slow markedly. These thought experiments stimulate curiosity about how life might adapt to extreme gravitational environments, even if such life is purely speculative. Time plays a central role in both cosmology and the physics of black holes. Near a black hole, gravitational time dilation means that time passes more slowly relative to distant observers. In the early universe, the rapid expansion during inflation stretched time intervals, smoothing out irregularities. The arrow of time emerges from entropy and expansion. Primordial black holes embody both extremes. They formed when time was young, yet they can slow time within their horizons. The interplay between time's flow and gravity invites contemplation about the nature of past and future. Singularities and cosmic censorship bring us back to the foundations of general relativity. A singularity is a region where curvature becomes infinite, and known physics breaks down. Cosmic censorship conjectures that singularities are always hidden behind horizons, preventing them from affecting distant regions. Primordial black holes test these ideas by forming in dynamic environments. Understanding whether horizons always form and what happens near singularities ties into quantum gravity and the ultimate fate of information. Looking far ahead, we ponder the fate of the universe and the role of black holes within it. If the universe continues to expand indefinitely, stars will burn out, galaxies will fade, and black holes will remain as some of the last massive objects. Over unimaginable timescales, even the largest black holes will evaporate, leaving only a bath of low-energy radiation. Primordial black holes, if they exist, could persist longer or shorter, depending on their masses. They would thus be among the final actors in the cosmic drama, connecting the dawn and the dusk of time. The study of primordial black holes exemplifies the synergy between observation and theory. Advances in detector sensitivity, data analysis, and theoretical modeling continually refine our understanding. Each new constraint narrows the possibilities, while each unexpected detection would open new avenues. The pursuit itself reflects a broader human endeavor to understand our origins and our place in the universe, using tools both mathematical and imaginative. As we near the end of this part of our journey, we pause to appreciate the richness of the story we have woven. We began with a universe just born, explored how tiny fluctuations could lead to black holes, and considered the myriad consequences these objects might have. Along the way, we moved from concrete equations to metaphors, from physical processes to philosophical reflections. This breadth mirrors the cosmos itself, which encompasses simplicity and complexity, clarity and mystery. The journey is not over. The questions we have raised about formation, detection, and significance remain open. Future observations will sharpen or alter our understanding. Theoretical developments may reveal new facets or propose entirely different mechanisms. As we continue into the next part, carry with you the curiosity and calm that have guided us. The next stage will build upon these foundations, inviting us to delve deeper into the mysteries of primordial black holes. Neutrinos offer another subtle probe. Primordial black holes, emitting or accreting matter, produce neutrinos as part of their particle output. In principle, the neutrino flux from evaporating black holes could be detected by large neutrino observatories. Although current detectors are not sensitive enough to pick out such a signal against the background of atmospheric and astrophysical neutrinos, future generations of detectors may achieve the necessary sensitivity. Their measurements would complement those of gravitational wave and electromagnetic observatories. On galactic scales, the presence of primordial black holes could influence the formation and stability of small structures like dwarf galaxies and globular clusters. These systems are dark matter dominated, and the insertion of compact objects could heat the stellar component or alter the density profile. Observations of star velocities and density distributions in these systems already place constraints on the abundance of massive compact objects. Continued surveys of dwarf galaxies and star clusters will sharpen these bounds. Stars themselves could capture primordial black holes. If a small black hole passes through a star, dynamical friction can cause it to lose energy and become gravitationally bound. Once inside, the black hole would sink to the core, where it could accrete stellar material. The energy released could affect the star's evolution, potentially leading to unusual luminosity or premature collapse. The absence of such anomalies in stellar populations constrains how frequently such captures can occur. Cosmic rays provide another perspective. Evaporating black holes emit high-energy particles, including electrons and positrons. These particles propagate through the galaxy, contributing to the cosmic ray spectrum. Instruments like AMS-02 and DAMPE measure cosmic ray fluxes with high precision. By comparing observed spectra with models of cosmic ray sources, scientists derive limits on the contribution from evaporating black holes, thereby bounding their abundance in the relevant mass range. The synergy between different detection methods underscores the ingenuity of scientific exploration. Astronomers and physicists employ telescopes, gravitational wave antennas, neutrino detectors, cosmic ray instruments, and precise timing of pulsars to piece together a picture of the universe. Each technique probes a different messenger: photons, gravitational waves, neutrinos, charged particles, or timing variations. Primordial black holes would leave traces in all these channels, and only by combining them can we hope to reveal or exclude their presence. Reflecting on the journey so far, one is struck by the interplay between certainty and speculation. Certain aspects of cosmology are well established, such as the expansion history and the success of Big Bang nucleosynthesis. Others, like the existence of primordial black holes, remain speculative. Yet speculation is not idle. It guides the formulation of hypotheses and motivates the search for evidence. The scientific method thrives on a balance between what we know and what we dare to imagine. As we prepare to move into the next chapter of our exploration, the horizon of knowledge appears both vast and inviting. The subject of primordial black holes encourages patience, diligence, and wonder. With each observation, each model, and each thought experiment, we inch closer to understanding whether these ghosts from the beginning of time are real. Whether they exist or not, the pursuit enriches our appreciation for the universe and for the process of discovery. Let us continue with minds open and hearts attuned to the subtle music of the cosmos. Among emerging techniques, the study of fast radio bursts offers an intriguing possibility. These millisecond duration flashes of radio waves originate at cosmological distances and can be bent and delayed by intervening masses. If a primordial black hole lies along the path of a burst, it could split the signal into multiple images with characteristic time delays. Detecting such lensing events requires precise timing and a large sample of bursts. But the field of radio astronomy is advancing rapidly. In the coming years, fast radio burst microlensing may provide yet another probe of compact objects. At a more fundamental level, primordial black holes invite us to think about the constants of nature. The Planck mass and Planck time set the scales at which quantum gravity becomes important. When we speak of a black hole evaporating down to a Planck mass remnant, or of collapse occurring when the horizon mass matches a certain value, we are invoking the interplay between constants like the speed of light, the gravitational constant, and Planck's constant. These constants underpin the very possibility of black holes and highlight the deep connections between different areas of physics. As we step forward, imagine the narrative continuing to unfold with the same gentle cadence. Each new idea will build on the foundation we have laid, and each new image will draw you further into the history of the cosmos. The mysteries we explore are profound, but our approach remains calm and reflective. In the next part, we will delve into additional facets of the story, maintaining the meditative tone and the slow pace that allows complex ideas to sink in. The journey through primordial black holes is far from over, and the wonder it inspires will accompany us onward. The universe expanded, and the echo of that ancient inflation still reverberates across the cosmos. Imagine the early fabric of spacetime stretching, smoothing out irregularities, while leaving behind tiny ripples. On the largest scales, these ripples are subtle, but on smaller scales, something extraordinary can happen. Certain patches of the inflating cosmos may have experienced brief phases where the slow, steady roll of the inflaton field faltered, causing the curvature spectrum to surge. Such interludes act like cosmic amplifiers, boosting quantum fluctuations into the seeds of future black holes. In the quiet of deep time, those amplified fluctuations waited patiently, frozen until the universe cooled enough for gravity to take over. Picture a landscape of energy where a field wanders across a plateau. When that field enters a region so flat that its motion nearly stops, the gravitational potential flattens too. During this ultra-slow roll epoch, fluctuations on scales exiting the horizon do not decay, but continue to grow. Long after inflation ends, when those modes re-enter the horizon during radiation domination, they reawaken as overdense islands ready to collapse. Other scenarios vary the effective sound speed of the fluctuations. A temporary reduction of this speed or rapid oscillations can resonate with the background, producing spikes in the power spectrum. Each feature in the spectrum is a fingerprint of a specific physical mechanism, carrying the imprint of early dynamics. Single-field models use these non-attractor phases to sculpt the spectrum. Multi-field models employ additional fields with their own dynamics. Imagine the inflaton coupled to a second field with a tachyonic instability, causing the secondary field to grow explosively and feed the primary fluctuations. During hybrid inflation, the so-called waterfall phase triggers rapid particle production that back-reacts on the inflaton. As the fields dance through the high-dimensional landscape, their trajectories may turn suddenly, mixing modes and boosting certain scales. Axion gauge field interactions are another exotic route. As gauge fields are produced, they source curvature perturbations, transferring their energy into metric fluctuations. Each of these pathways leads to a temporary, yet dramatic increase in the curvature spectrum at specific wave numbers. Most of these enhancements require the spectrum to be blue at small scales or to feature a narrow peak, while the cosmic microwave background reveals a red tilt, more power on large scales. The formation of primordial black holes demands an opposite trend on tiny scales. When a spike arises at some comoving wave number, it corresponds to a particular horizon mass at the time those modes re-enter. A narrow peak means that all potential black holes will have similar masses. The amplitude of this peak must be high because only the largest overdensities collapse. A slight change in amplitude drastically alters the fraction of regions that cross the threshold. The rarity of the event means that the probability distribution's tail determines how many black holes form. Consequently, the physics of inflation must be carefully tuned to produce just the right amount of enhancement without overproducing or underproducing black holes. As inflation ends and the universe transitions into a hot, radiation-dominated phase, the geometry is nearly uniform, but not perfectly so. Tiny curvature perturbations remain, each carrying a memory of the inflating epoch. To estimate when and where collapse occurs, cosmologists smooth the density field over different scales. They often use the three-zone model, a closed overdense region surrounded by a compensating underdense region, all embedded in a flat background. In this picture, the key quantity is the density contrast at horizon crossing. If an overdense region has a contrast above a critical threshold, gravitational pull overwhelms pressure forces, and the region collapses into a black hole. Below this threshold, the region simply disperses or virializes into small fluctuations. The threshold depends on the equation of state of the dominant matter. During radiation domination, pressure gradients resist collapse, raising the threshold. To understand collapse more precisely, researchers use the concept of the compaction function. It measures the mass excess within a spherical shell relative to the average background mass, divided by the areal radius. When the compaction function reaches its maximum, that radius marks the location most prone to collapse. The average of this maximum across different shells leads to a universal threshold. In a radiation-dominated universe, this critical averaged compaction corresponds to a density contrast of roughly 40%. If the compaction is lower, pressure will disperse the overdensity. If higher, gravity wins. Remarkably, this threshold is largely independent of the specific shape of the perturbation. The local curvature at the peak, rather than the global profile, determines whether a black hole forms. Peaks theory then enters the story. Each peak in the curvature field corresponds to a potential collapse site. Its height and curvature determine its fate. High peaks above the critical compaction collapse quickly, while lower peaks do not, because the distribution of peaks falls off steeply with height. Only the rarest peaks produce black holes. The interplay between local geometry and the surrounding environment defines the outcome. A smooth peak, surrounded by a compensating underdensity, may still collapse if its central curvature is sufficiently sharp. Conversely, a broad peak might fail to collapse, even if its average density is high, because pressure gradients can disperse the matter. Understanding these nuances requires careful analysis of the local geometry, rather than simple global averages. As a fluctuation approaches the collapse threshold, it enters a regime governed by critical phenomena. At this boundary between dispersal and collapse, small differences in amplitude lead to dramatically different masses. Numerical simulations reveal that the black hole mass scales as the difference between the density contrast and the critical value raised to a universal exponent. This exponent, roughly 1/3 for a radiation fluid, is independent of the initial profile. The closer the fluctuation is to the threshold, the smaller the resulting black hole. Conversely, fluctuations far above the threshold produce black holes close to the horizon mass. This scaling relation means that even if the horizon mass is large, a continuous spectrum of smaller masses emerges from near-critical perturbations. Critical collapse therefore broadens the mass function. Instead of all black holes having the same mass, there is an extended distribution that depends on the statistics of the initial fluctuations. A narrow peak in the power spectrum still leads to a relatively narrow mass function, but the tail becomes extended. This reduction in average mass decreases the fraction of the universe that can collapse into black holes, because many near-threshold fluctuations produce only tiny black holes. The mass function also depends on how many different horizon masses contribute. If the power spectrum has a broad shape, fluctuations at different scales produce black holes at different times. Combining the spread from multiple horizon masses with the spread from critical collapse yields a rich spectrum of masses. Understanding this distribution is essential when comparing models to observations, as gravitational waves and micro-lensing surveys are sensitive to different mass ranges. The early universe was not only characterized by smooth radiation, it underwent dramatic phase transitions as fundamental forces separated and particles acquired mass. Some of these transitions may have been first order, involving the nucleation of bubbles of a new vacuum state. Picture a sea of high-energy vacuum where bubbles of lower energy appear spontaneously and expand at near the speed of light. As they grow, their walls collide and release energy. In rare circumstances, two or more bubbles with nearly horizon size and thick walls can collapse upon collision, concentrating enough mass in a compact region to satisfy the collapse criteria. When the walls meet, the energy density temporarily exceeds the background by a large margin, forming a black hole. The mass of a black hole formed by colliding bubbles depends on the size of the bubbles at collision. In many models, the resulting mass distribution is nearly monochromatic because bubbles of similar size nucleate at a characteristic scale. Phase transitions can also soften the equation of state, reducing the pressure support in the plasma. For example, during the transition associated with the breaking of the electroweak or QCD symmetries, the effective sound speed drops. Lower pressure means that even moderately overdense regions can collapse. Thus, the timing of the phase transition and the physics of the vacuum determine whether the conditions are favorable for black hole formation. Although bubble collisions are rare, the resulting black holes could contribute significantly to the dark matter if their abundance and mass are appropriate. Another route to primordial black holes comes from topological defects created during symmetry breaking. In the early universe, scalar fields acquiring different values in disconnected regions can lead to cosmic strings and domain walls. Cosmic strings are one-dimensional objects with immense tension that can thread through the cosmos like filaments. When the network of strings intersects itself, loops form and oscillate, radiating gravitational waves. Occasionally, small loops may collapse into black holes if their energy density within a loop radius is high. Moreover, strings can attach to existing primordial black holes, forming nets that oscillate and shrink due to the emission of gravitational radiation. These nets can cause black holes to merge or move through space in unexpected ways, dragging strings into galactic centers or keeping black holes from joining dark matter halos. Domain walls arise when discrete symmetries break. They are two-dimensional surfaces separating regions of different vacuum states. Horizon-scale domain walls can dominate the energy density, if they persist for too long, leading to cosmological problems. However, if a small bias eventually drives the walls to collapse, their energy releases can form black holes. Fluctuations in the number density of domain walls within a horizon volume can cause some regions to have more walls than average. When the ratio of domain wall energy density to radiation approaches a critical value, roughly 1/10, these fluctuations collapse into black holes. While this mechanism is speculative, it illustrates how diverse and exotic the early universe might have been. Each topological defect offers a unique path toward compact object formation, expanding the possibilities beyond simple overdensities. The picture becomes even richer when considering departures from Gaussian statistics in the initial fluctuations. Standard treatments often assume that the perturbations follow a Gaussian distribution, which is a reasonable approximation for the scales probed by the cosmic microwave background. Yet primordial black hole formation probes the far tail of the distribution. Here, even tiny deviations from Gaussianity can produce huge differences in the probability of collapse. A slight skewness or kurtosis modifies the abundance of rare peaks, either enhancing or suppressing black hole formation. In models where the perturbations derive from nonlinear processes, the distribution may be heavily skewed. For instance, if the curvature perturbation originates from the square of a Gaussian field, it follows a chi-squared distribution. Such non-Gaussian statistics increase the probability of large fluctuations, reducing the required amplitude of the power spectrum. The effect of non-Gaussianity can be dramatic. When using Gaussian statistics, the required amplitude of the curvature power spectrum for black hole formation is typically of order 1%. A small reduction in the threshold or a small change in amplitude can shift the fraction of collapsing regions by many orders of magnitude. Introducing non-Gaussianity can lower the necessary amplitude by a factor of 10 or more. This sensitivity means that any complete model of primordial black hole formation must account for the detailed shape of the probability distribution. Non-Gaussianities may arise naturally in models with multiple fields, resonant particle production, or interactions that generate higher-order correlations. They may also be inevitable because the very act of collapsing into black holes introduces a Poisson distribution of number fluctuations, which itself induces isocurvature modes. Statistical rarity also implies that primordial black holes form in isolated pockets. Most regions of the universe never become sufficiently overdense. Those few that do may cluster or remain scattered, depending on the scale of the fluctuations. If the fluctuations are extremely peaked, the black holes form almost simultaneously with similar masses, leading to a monochromatic distribution. If the spectrum is broad and the statistics are non-Gaussian, formation times and masses vary, creating an extended mass function. In both cases, the distribution of black holes imprints itself on the gravitational wave background and the pattern of isocurvature perturbations. Understanding these statistical properties is essential for connecting theoretical models to observations of gravitational waves, microlensing events, and the cosmic microwave background. Having explored the processes that give birth to primordial black holes, one must consider their fate. Black holes are not eternal in classical general relativity, and quantum mechanics adds further intrigue. According to Hawking's prediction, black holes radiate particles due to quantum effects near the event horizon. This radiation causes them to lose mass over time. For stellar mass or larger black holes, the evaporation time exceeds the age of the universe by many orders of magnitude. For smaller primordial black holes, however, evaporation can be significant. Those with masses below roughly 1 billion tons would have completely evaporated by now, releasing their energy as a final burst of particles. During their evaporation, primordial black holes can produce exotic particles, Super-weakly interacting, or supermassive relics, impossible to create in conventional particle physics experiments, might emerge from the high-temperature environment near the end of evaporation. Stable remnants could survive as dark matter candidates. Although speculative, this idea provides an avenue for linking the physics of primordial black holes to the properties of dark matter. The evaporation process also contributes to the cosmic backgrounds of gamma rays, neutrinos, and gravitational waves. Observational constraints from these backgrounds limit the abundance of light, primordial black holes, indirectly shaping the viable formation scenarios. For primordial black holes, massive enough to survive evaporation, their subsequent evolution is governed by gravity and interactions with their environment. Some may merge with each other, producing gravitational waves. In certain scenarios, black holes formed at high density may cluster, increasing the merger rate. Others may capture surrounding matter or be dragged by cosmic strings into dense regions. The presence of string networks or domain walls can influence their distribution. Mergers not only alter the mass spectrum, but also generate gravitational wave signals that we might detect today. These signals provide another window into the early universe, complementing the electromagnetic constraints. Over cosmic time, the fraction of primordial black holes that persist depends on their initial mass function, their merger history, and the rate at which they interact with other compact objects. Some may be captured by stars, or sink toward the centers of galaxies. Others might remain isolated in the outskirts of galaxies, or in intergalactic space. The interplay between evaporation, mergers, and gravitational interactions determines whether primordial black holes can constitute a significant fraction of dark matter. If they are too light, they evaporate. If they are too heavy, their abundance may be constrained by microlensing and dynamical observations. Yet there remains a window in parameter space where they could still account for the unseen mass of the universe. The story of primordial black holes thus unfolds across multiple epochs and involves a tapestry of physical processes. Inflation lays the groundwork by sculpting the primordial power spectrum. Local geometry and critical phenomena determine which overdense regions collapse. Phase transitions, bubble collisions, and topological defects provide alternate routes to compact objects. Non-Gaussian statistics shape the probability of rare peaks. Evaporation, mergers, and interactions decide how many black holes survive to the present day. Each chapter adds depth to the narrative, revealing how delicate the balance must have been for these ghostly objects to exist. In this serene exploration, the cosmos feels like a living entity, full of complex dynamics, yet governed by elegant principles. We have wandered through the early inflationary landscapes, lingered at curvature peaks, contemplated the threshold of collapse, and witnessed the violent unions of bubbles and defects. We have glimpsed the subtle mathematics of probability distributions and the quantum whispers of Hawking radiation. The path continues onward, deeper into the unknown, with more phenomena waiting to be uncovered and understood. As the narrative flows gently forward, it invites reflection on the profound interconnectedness of physical processes and the enduring mystery of the dark universe. The hunt for primordial black holes extends into the realm of gravitational waves. Modern detectors listen for ripples in spacetime produced by merging black holes. Ordinary stellar remnants have masses above a few solar masses and circularize before merging. But a primordial origin could lead to subsolar mass binaries or mergers with significant eccentricity. Searches for such unusual signals have been conducted, but so far no compelling candidates have been found, placing upper limits on the abundance of light primordial pairs. When many primordial black holes exist, they would form binaries early and merge frequently. The gravitational waves from these events would superimpose to create a cosmic background. Observatories like LIGO and Virgo measure the merger rates of black holes and place constraints by requiring that the predicted merger rate from primordial binaries does not exceed the observed rate. In addition, the non-observation of a stochastic gravitational wave background strongly limits the fraction of dark matter that primordial black holes can comprise in certain mass ranges. Future gravitational wave observatories promise to expand this search. Planned space-based detectors will be sensitive to lower frequencies, while terrestrial instruments will see higher masses with greater clarity. These instruments will not only detect individual events, but may also reveal the cumulative background from countless mergers. If a gravitational wave background is eventually detected, its spectral shape and amplitude could distinguish between astrophysical and primordial origins. Fast radio bursts offer another intriguing probe of primordial black holes. These millisecond-long flashes originate in distant galaxies and arrive at Earth as isolated, bright pulses. If a compact object lies along the line of sight, its gravity could split the burst into two images separated by a time delay comparable to the burst duration. Analyses of hundreds of bursts have yielded only one candidate, suggesting that any contribution from 10 solar mass primordial lenses must be modest. Detailed modeling of fast radio burst lensing reveals a complex parameter space. The magnification and time delay depend on the burst's intrinsic width, the lens mass, and the alignment. Observational campaigns must account for these factors to avoid confusion with intrinsic variability. As catalogues grow and time resolution improves, the chances of detecting a clear lensing event increase. Another lensing phenomenon involves caustic crossings. As a compact object moves relative to a background source, the magnification peaks sharply when the source passes through a caustic curve formed by the lensing geometry. In radio or optical transients, this can produce brief, intense flares. Detecting such events requires continuous monitoring and careful timing, but they could provide precise mass measurements of the lens. The wave nature of light introduces additional signatures. When the Schwarzschild radius of a lens is comparable to the wavelength, interference patterns appear in the energy spectrum of the background source. This femtolensing regime was explored using gamma-ray bursts, and the absence of interference fringes constrains the abundance of primordial black holes, holes in the mass range of roughly 5 times 10 to the 17th to 10 to the 20th grams. Detecting such interference would not only confirm a lensing event, but also reveal the tiny mass of the lens. Microlensing surveys have long searched for compact dark matter by monitoring the brightness of stars. Most events are due to ordinary stars and remnants, but occasionally ultra-short duration events occur. A handful of these could be explained by Earth mass lenses, leading to speculation about primordial origins. Nonetheless, the overall population statistics show that only a small fraction of dark matter can be in the form of primordial objects in the mass range from roughly 10 to 10 solar masses to a few solar masses. Further dynamical footprints arise in star clusters and wide binary systems. Massive compact objects moving through a cluster transfer kinetic energy to stars, heating the cluster and potentially dissolving it over cosmic time. Similarly, wide binaries in the galactic halo are fragile. Encounters with heavy lenses can disrupt these loose pairs. Observations of surviving binaries therefore place tight limits on how many primordial black holes can inhabit the halo. Accretion onto primordial black holes offers a window into their presence at much later times. Gas falling into a compact object releases radiation, And if many primordial black holes existed, their combined emission could distort the cosmic microwave background. Early analyses predicted strong distortions, but later work with more realistic accretion models yields milder constraints. Measuring subtle spectral deviations remains a powerful test, but uncertainties in accretion physics complicate the interpretation. Coordinating observations across multiple messengers enhances the search. A burst of neutrinos detected in coincidence with a gamma-ray flash and a gravitational wave could be a smoking gun. Each messenger travels differently through the cosmos, offering complementary information. Combining data sets allows scientists to cross-check signals and reduce false positives, improving the chances of isolating a primordial origin. Even with multiple messengers, astrophysical backgrounds pose challenges. Merging neutron stars, magnetar flares, supernovae, and active galactic nuclei all produce high-energy emissions. Disentangling a primordial signal from this cacophony requires careful modeling of every known source. This modeling must be continually updated as new phenomena are discovered. Large simulations help anticipate the signatures of primordial black holes. By populating synthetic universes with hypothetical lenses, researchers can predict the distribution of microlensing events, gravitational wave signals, and transient lensing rates. The simulations are informed by the latest observational constraints and explore how different mass functions and spatial distributions affect the signals. Comparing these predictions with data provides a statistical framework for inference. Statistical approaches also allow stacking data from many events. In gravitational wave astronomy, stacking dozens of sub-threshold signals can reveal a population that is individually too weak to detect. Similarly, stacking many fast radio bursts or gamma-ray transients increases sensitivity to weak lensing effects. This collective analysis requires careful treatment of noise and systematics, but it can uncover subtle trends. Beyond photons and gravitational waves, the cosmic 21-centimeter line from neutral hydrogen offers a complementary probe. Primordial black holes could influence the temperature of the intergalactic medium through accretion or energy injection. These effects would alter the absorption and emission features of the 21-centimeter line during cosmic dawn. Future radio arrays aim to map this signal across the sky, potentially revealing indirect signatures of compact dark matter. Another subtle effect arises from gravitational wave memory, a permanent distortion in spacetime left behind after a burst. In principle, repeated mergers of primordial black holes could create small but cumulative offsets in the positions of test masses. Detecting such memory would require precise timing and calibration of gravitational wave detectors. While speculative, it underscores the range of phenomena that might betray the presence of these objects. Probing the early universe also involves searching for high redshift quasars and galaxies. If primordial black holes acted as seeds for early structure, they could accelerate the formation of massive black holes in the first billion years. Observations with next-generation telescopes may uncover an abundance of unexpectedly massive objects at high redshift. This would hint at the role of primordial seeds in cosmic history. Instrumental advances will shape the future of the search. Ground-based optical surveys, like the Vera Rubin Observatory, will monitor billions of stars for microlensing events. Space missions, like Euclid and the Nancy Grace Roman Space Telescope, will map the sky with unprecedented detail, enhancing our ability to detect tiny brightness fluctuations. Radio arrays will expand fast. Radio burst catalogues and gravitational wave observatories will refine their sensitivity and frequency coverage. Among the planned gravitational wave missions, the Laser Interferometer Space Antenna will open a new low-frequency window. It will detect mergers of massive black holes and long-period binaries, potentially including primordial systems not accessible to ground-based detectors. The combination of space and ground-based data will allow a more complete reconstruction of the merger history of compact objects. If primordial black holes contribute significantly, their imprint will appear in these datasets. Radio telescopes will continue to revolutionize our understanding of transient phenomena. Arrays like CHIME, DSA, and the upcoming SKA will harvest thousands of fast radio bursts, enabling high-precision studies of lensing statistics. Monitoring repeating sources will help identify subtle echoes and periodicities, while polarization measurements may offer clues about the lensing geometry. The interplay between theory and observation in radio astronomy is poised to deepen. Neutrino observatories are also evolving. Upgrades to existing detectors and new instruments such as IceCube Gen 2 and KM3 NET will increase sensitivity to high-energy neutrinos. These detectors will be better able to distinguish neutrino flavors and reconstruct the direction and energy of incoming particles. Combining their data with gamma-ray and gravitational wave observations will strengthen multi-messenger analyses. High-energy gamma-ray observatories will complement these efforts. Facilities like the Cherenkov Telescope Array will detect faint and distant gamma-ray sources with improved angular resolution. This will refine measurements of diffuse backgrounds and transient events. Should a primordial black hole explode nearby, such a telescope would capture the gamma-ray flash with unprecedented clarity. Cosmic ray detectors like AMS and future missions will continue to monitor the flux of antimatter in space. Enhancements in energy resolution and particle identification will improve the ability to search for anomalies. If a population of tiny black holes is evaporating, their contribution to the antiproton or positron flux could become more apparent. However, astrophysical uncertainties, such as the propagation of cosmic rays through the galaxy, remain a limiting factor. The gravitational wave background is not the only diffuse signal of interest. A cosmic neutrino background also exists, originating from past astrophysical events and possibly from primordial black hole evaporation. Detecting this diffuse neutrino sea is challenging, but future experiments aim to probe the energy range where such contributions might be significant. Success would open another window on cosmic history and particle physics. The cosmic microwave background continues to be a goldmine of information. Precision measurements of its temperature and polarization reveal subtle features that trace the early universe's dynamics. A population of primordial black holes would have injected energy, altered ionization histories, and modified the anisotropy spectra. Ongoing and future missions strive to detect or constrain such effects with ever greater precision. Dark matter remains one of the great mysteries of modern physics. Primordial black holes are one candidate among many, including weakly interacting massive particles and axions. Each candidate brings its own set of detection strategies and theoretical challenges. Exploring all possibilities enriches our understanding and guards against premature conclusions. Interactions between dark matter and baryons can also produce observable consequences. If primordial black holes interact gravitationally with gas clouds, they could create wake structures or alter star formation rates. Simulations of these interactions help predict potential signatures. Observations of molecular clouds and star-forming regions might reveal such imprints. The search for primordial black holes intersects with the study of exoplanet microlensing. Surveys looking for planets around distant stars are sensitive to any compact objects along the line of sight. Transits and microlensing events can reveal the presence of objects much smaller than stars. Cross-analysis of planetary surveys and dark matter searches may yield mutual benefits. Astrometric microlensing offers yet another technique. Rather than measuring brightness changes, this method detects tiny shifts in the apparent position of a background star as a lens passes nearby. Instruments like Gaia are capable of measuring such small astrometric deflections. The combination of photometric and astrometric data strengthens the identification of lenses and can provide direct mass estimates. In the realm of time-domain astronomy, new phenomena continue to emerge. Unexpectedly fast transients, repeating radio bursts with complex substructure, and mysterious optical flares all challenge our models. Some of these may be unrelated to primordial black holes, but still inform us about the extreme universe. Keeping an open mind helps researchers recognize novel signatures that might otherwise be overlooked. Gravitational microlensing of quasars and radio jets provides complementary constraints at higher lens masses. Variability in quasar light curves on timescales of months to years can reveal the presence of planetary mass lenses. Radio interferometers can detect millilensing distortions in jet morphology. Together, these observations probe mass ranges not accessible to gamma-ray or optical microlensing. Cosmologists also study topological defects like cosmic strings, which can produce lensing signatures similar to those of compact objects. Distinguishing between a string and a primordial black hole requires careful analysis of the lens geometry and the resulting light curve. The diversity of possible lenses reminds us to consider all exotic phenomena when interpreting data. Such breadth ensures that we do not misidentify one type of new physics for another. Theoretical work on modifications of gravity can influence the interpretation of microlensing and gravitational wave observations. Alternative theories of gravity often alter the lensing properties of compact objects or modify wave propagation speeds. Constraints derived assuming general relativity may need to be revisited if these theories prove viable. Thus, fundamental physics and astrophysical observations are deeply intertwined. Inflationary models of the early universe can produce enhanced density fluctuations that seed primordial black holes. The shape and amplitude of these fluctuations depend on the inflationary potential and reheating processes. Observational constraints on primordial black hole abundance therefore feed back into model building in cosmology. Conversely, future data may favor specific inflationary scenarios that naturally produce a certain mass range of black holes. Particle physics may also leave its mark. If heavy stable particles exist, they could decay or annihilate and influence primordial black hole production. Neutrino masses and mixing angles affect energy injection and cooling rates, altering the conditions under which black holes form. The interplay between particle physics and cosmology continues to be a fertile ground for exploration. In addition to mergers, primordial black holes could capture stars or planets. This would lead to observable disruptions, such as sudden brightening or the ejection of stellar material. Detecting such interactions requires monitoring millions of stars over long periods. Upcoming time-domain surveys will increase the chance of seeing these rare events. Cosmic magnetic fields may also play a role in the accretion behavior of primordial black holes. Magnetic turbulence can channel gas flows, enhancing or suppressing accretion rates. Understanding these processes is critical for interpreting radiation signatures. Radio polarization measurements could provide indirect constraints on such magnetic effects. The near field offers unique opportunities too. Local microlensing surveys within our galaxy can detect objects with masses as low as that of the Moon. These observations test the small mass end of the primordial black hole mass spectrum. Combining data from different stellar populations helps build a comprehensive picture. High-energy astrophysical neutrinos, detected by experiments like IceCube, originate from cosmic accelerators. If primordial black holes emit neutrinos during explosive evaporation, they could contribute to this high-energy population. Distinguishing such contributions from astrophysical sources involves careful spectral analysis and modeling. The isotropic distribution of high-energy neutrinos provides a broad canvas for such studies. Astrophysical gravity waves are not the only signals to consider. The formation of large-scale structure generates gravitational potential fluctuations that cause subtle distortions in the cosmic microwave background through the integrated Sachs-Wolf effect. Primordial black holes could modulate these potentials locally. Although these effects are tiny, they add to the rich tapestry of signatures that can be explored with precise measurements. The morphological features of lensing events contain hidden information. Light curves with characteristic peaks and valleys, frequency-dependent fringes, and polarization changes all encode details about the lens. Machine learning techniques can be trained to recognize these patterns. This integration of artificial intelligence into astronomy is accelerating discoveries across the board. Cross-correlations between different data sets often reveal surprises. For example, matching the positions of gamma-ray bursts with gravitational wave events has already uncovered joint detections. Similar correlations between fast radio bursts, neutrinos, and microlensing could highlight new physical connections. Maintaining comprehensive, publicly accessible databases facilitates such analyses. Serendipity plays an important role in discovery. Many breakthroughs arise not from targeted searches, but from anomalies noticed by attentive observers. The field of primordial black hole research benefits from a culture that values curiosity and open exploration. Encouraging diverse perspectives increases the chance of spotting the unexpected. There are ethical considerations as well. Designing, constructing, and operating large astronomical facilities requires substantial resources. Ensuring equitable access and balancing environmental impacts with scientific benefits are important discussions. Public support for fundamental science hinges on transparency and inclusion. Education and outreach help demystify the search for primordial black holes. Communicating the excitement and challenges of the field inspires the next generation of scientists. Outreach programs that explain complex concepts through analogies and visualizations bring abstract ideas to a broader audience. This broader engagement enriches society's appreciation of the cosmos. Interdisciplinary collaboration is a hallmark of contemporary astrophysics. Physicists, astronomers, engineers, data scientists, and philosophers all contribute to the quest. Workshops and conferences bring together diverse expertise, fostering cross-fertilization of ideas. This collaborative spirit underpins the progress that has been made and will continue to drive innovation. The cultural impact of black hole research extends beyond science. Artists, writers, and musicians are inspired by the notion of invisible objects shaping the universe. Stories that weave together facts and imagination bring these ideas into the public consciousness. Such creative expressions reflect humanity's enduring fascination with the unknown. As we expand our observational reach, new questions emerge. What role do primordial black holes play in the chemical evolution of galaxies? Could they influence the distribution of heavy elements? Investigating these questions requires integrating astrophysical theory, nucleosynthesis models, and observational data. There is also the possibility that primordial black holes could coalesce with white dwarfs or neutron stars. Such encounters might trigger unusual explosions or lead to exotic compact remnants. Detecting these events would open a new chapter in transient astronomy. Theoretical studies explore scenarios where such interactions could occur. New computational techniques are enhancing our ability to interpret data. Bayesian inference, machine learning, and high-performance computing allow us to explore complex parameter spaces. These methods help quantify uncertainties and distinguish between competing hypotheses. The synergy between computational advances and observational data drives the field forward. Feedback between theory and experiment is vital. Unexpected observations challenge existing models and prompt refinements or entirely new theories. Conversely, theoretical predictions motivate new observations and experimental designs. This iterative process, at the heart of scientific progress, is vividly illustrated in the search for primordial black holes. At the edge of this exploration lie philosophical questions about the nature of space, time, and existence. Studying primordial black holes touches on quantum gravity, the information paradox, and the origins of the universe. While these questions may seem abstract, they influence how we interpret empirical results. Embracing this philosophical dimension enriches the scientific narrative. Speculation must always be tempered by evidence. The absence of a signal is itself a meaningful result, narrowing the range of possibilities. Patience is required when searching for phenomena that might be rare or subtle. The history of science shows that persistence often pays off in unexpected ways. As we look ahead, we imagine a future where multi-messenger astronomy becomes routine. Instruments will operate in concert, sharing alerts in real time and enabling rapid follow-up across the spectrum. Data archives will be interconnected, allowing seamless cross-analysis. In such a world, the subtle signatures of primordial black holes may finally be teased out. The final answers may still be far away, but the journey itself is enriching. Every null result refines our understanding and guides us toward more fruitful avenues. The process teaches resilience and adaptability. Above all, it reflects humanity's deep desire to comprehend the universe. New particles such as axions and sterile neutrinos are being sought through a variety of experiments. Although these particles are unrelated to black holes, the techniques developed to detect rare events often overlap. Sensitive detectors that monitor faint signals must discriminate between background noise and true events. Lessons learned from these experiments inform strategies for identifying subtle signatures of primordial black holes. On Earth, particle accelerators probe fundamental interactions at unprecedented energies. While the energies involved are far below those found near black holes, colliders help test theories of the early universe. Insights into symmetry breaking, matter-antimatter asymmetry, and particle decays feed back into cosmological models. This crosstalk between terrestrial and astrophysical experiments enriches both fields. Theoretical frameworks beyond the standard model of cosmology provide fertile ground for speculation. String theory, loop quantum gravity, and models with extra dimensions offer novel mechanisms for black hole formation and evaporation. Exploring these possibilities requires careful mathematics, but also guidance from observation. Even without direct detection, constraints on primordial black holes help narrow the landscape of viable theories. Philosophical discussions accompany these scientific efforts. The idea that the universe might contain relics from its earliest moments raises questions about determinism and chance. Some ponder whether the distribution of primordial black holes could influence the emergence of life. Such contemplations remind us that science not only seeks to measure, but also to understand our place in the cosmos. Finally, the complexity of the universe ensures that surprises await. Signals may arise from phenomena we have not yet imagined. Remaining open to unexpected connections across disciplines increases the likelihood of discovery. As observations accumulate and theories evolve, the tapestry of clues will grow richer, guiding us toward deeper insights about the dark fabric of the universe. In the darkness between galaxies, the passage of a primordial black hole becomes a quiet event. We cannot see such an object directly, yet we imagine it as a speck of pure gravity wandering through the cosmos. What betrays its presence are the whispers of energy it leaves behind. Detecting those whispers is like listening for the last note of a song fading into the night. The smallest of these relics are expected to evaporate in a blaze of energy through a process called Hawking radiation. As they lose mass, their temperatures rise, and the final stage of their lives may end with a burst of high-energy particles. These final fireworks could include gamma-ray photons, neutrinos, electrons, positrons, and even antiprotons. The theoretical brilliance of such a moment is alluring, but the challenge lies in distinguishing these signals from the cosmic background. Imagine a primordial black hole reaching the end of its life somewhere in the Milky Way. According to particle physics, the cascade of particles it releases would flood space with energies far beyond what humans can replicate in laboratories. Among these particles, neutrinos are particularly interesting because they travel unimpeded through matter and carry signatures of the explosion unchanged. If a neutrino observatory were to register a burst of unusually energetic neutrinos, we might be witnessing the death throes of a tiny black hole. High-energy telescopes on Earth and in orbit constantly monitor the sky for gamma-ray bursts. A primordial black hole's last moments could mimic a short gamma-ray flash, but nature produces many such flashes from exploding stars and merging neutron stars. Scientists use sophisticated algorithms to search for bursts with specific energy spectra predicted by Hawking's theory. So far, these searches have not revealed a definitive signal, providing upper bounds on how many black holes of a given mass could be evaporating today. The universe also supplies us with cosmic rays, particles that rain down on our planet from all directions. Among them are antiprotons and positrons, which may originate from the decay of very small black holes. Instruments on balloons and satellites measure the flux of these particles and compare it to models of cosmic ray production. A surplus of antimatter could hint at a hidden population of primordial evaporators. While photons and charged particles interact with interstellar gas and magnetic fields, neutrinos offer a cleaner signal. They pass through gas, dust, and even entire planets, barely interacting with anything. This property allows neutrino telescopes, like IceCube in Antarctica or future detectors in space, to probe deep into the galaxy. Such observatories have wide fields of view and almost no dead time, making them excellent instruments for catching rare bursts. One study of an extremely energetic neutrino measured at Earth suggested it might have come from a primordial black hole's explosion. The probability of such a coincidence is small, but it fuels the imagination. If many more neutrinos with similar energies arrived from different directions and at different times, the case would grow stronger. For now, each candidate event serves as both inspiration and motivation for continued monitoring. Hawking radiation also produces a continuous background of photons at energies lower than the explosive end stage. These emissions contribute to diffuse gamma-ray backgrounds observed by telescopes like Fermi LAT. By analyzing the spectrum of this background, scientists set limits on how many small primordial black holes can exist. If there were too many, the combined emission would exceed what we observe. Antimatter signatures offer another avenue. Experiments such as the Alpha Magnetic Spectrometer on the International Space Station monitor the ratio of antiprotons to protons. Excess antiprotons could hint at exotic sources, including evaporating black holes. Yet astrophysical processes like supernovae can also produce antimatter, so interpreting the data demands careful modeling. The search for Hawking radiation is not limited to high-energy cosmic messengers. On the scale of the early universe, primordial black hole evaporation could have heated the cosmic plasma and left imprints in the cosmic microwave background. Such heating would slightly modify the spectrum of the relic radiation that fills the cosmos. Observations of the microwave sky help set constraints on the number and mass of evaporating black holes. Even if we do not detect direct bursts, we can infer the existence of tiny black holes through the absence of a signal. Null results from gamma-ray telescopes, cosmic ray detectors, and neutrino observatories translate into upper limits on how abundant these objects can be. Each new generation of instruments pushes these limits lower. The silence of the universe becomes a measurement in itself. As we move from subatomic particles to the domain of light, gravitational lensing emerges as a powerful tool. When a compact object passes in front of a distant source, its gravity bends the light and can produce subtle or dramatic effects. In the extreme regime, where the lens is much smaller than the wavelength of the light, quantum interference patterns arise. This phenomenon, known as femtolensing, can reveal black holes weighing between 1 billion and 1 quadrillion kilograms. Gamma-ray bursts, with their brief flashes of intense light, provide natural sources for femtolensing. If a primordial black hole lies near the line of sight to such a burst, the interference pattern would imprint oscillations in the burst's spectrum. Astronomers have analyzed hundreds of bursts with this possibility in mind. Thus far, no interference signatures have been found, implying that very low-mass black holes cannot make up a significant fraction of dark matter. Moving up in mass, the lensing effect becomes easier to detect. In microlensing, the gravitational field of the lens magnifies and brightens the background source without splitting it into separate images. Surveys like the Optical Gravitational Lensing Experiment, OGLE, and its predecessors have monitored millions of stars in the Milky Way and nearby galaxies. When a compact object passes in front of a star, the star brightens in a characteristic way. By analyzing these light curves, researchers infer the number and mass of potential lenses. Microlensing surveys have placed strong constraints on primordial black holes across a broad range of masses. In the range from about 1/10 of a solar mass to a few solar masses, lensing events are relatively common if such black holes existed in large numbers. The fact that most observed events are consistent with ordinary stars and remnants means primordial black holes cannot comprise more than about 10% of the dark matter. This result covers the mass window associated with the quantum chromodynamics phase transition, which is a popular formation epoch. Despite the stringent limits, some intriguing hints persist. Among the thousands of microlensing events recorded by OGLE, a handful have extremely short durations. These ultra-fast events could be caused by low-mass lenses, such as free-floating planets or Earth-mass primordial black holes. If the latter interpretation were correct, the data would suggest a small but non-zero fraction of dark matter composed of such objects. Follow-up observations of the Andromeda Galaxy might help distinguish between these possibilities. At slightly higher masses, millilensing becomes relevant. Here, The lensing object is heavy enough to create multiple images of a background source, but the separation is too small to resolve with present telescopes. Instead, astronomers look for distortions in radio jets and anomalous flux ratios in quasars. These subtle effects could betray black holes with masses of thousands to millions of solar masses lurking along the line of sight. Gravitational lensing is attractive because it depends only on the mass of the lens and the alignment of the source. It is insensitive to the composition of the object, whether it is made of baryonic matter, dark matter, or something more exotic. This purity makes lensing a clean method for searching for primordial black holes. Yet the absence of a positive detection is a powerful constraint on their abundance. As we zoom out from individual stars to larger systems, the dynamical effects of primordial black holes come into focus. In a stellar cluster, a population of massive black holes would stir up the motions of stars, heating the cluster and possibly causing it to dissolve. Observations of globular clusters and dwarf galaxies show that these systems are surprisingly fragile and long-lived. This longevity implies that any hidden massive objects cannot be too numerous or too massive. Wide binaries, stellar pairs separated by distances comparable to our solar system, offer another sensitive probe. Such pairs are easily disrupted by passing compact objects. The continued existence of wide binaries in the galactic disk constrains how many primordial black holes with tens of solar masses can be present. If such black holes were abundant, we would see fewer widely separated stars than we do. On an even grander scale, the thin disks of spiral galaxies provide a record of gentle gravitational interactions. Their vertical thickness reflects how much they have been heated over billions of years. A population of heavy primordial black holes passing through the disk would pump energy into the stellar orbits, puffing up the disk. The observed thinness of many disks therefore limits the number of such intruders. These dynamical arguments complement lensing and particle detection. While lensing is sensitive to the presence of an object along a specific line of sight, dynamical heating reflects the cumulative effect of many encounters over time. Each method probes a different aspect of the dark matter population. Together, they weave a tight net through which only a small fraction of primordial black holes can slip. Another subtle imprint of primordial black holes comes from their interactions with cosmic gas. As a black hole moves through the interstellar medium, it accretes material and converts some of it into radiation. In the early universe, accretion onto primordial black holes could have heated and ionized the surrounding gas. This process would alter the cosmic microwave background and the spectrum of hydrogen emission. The cosmic microwave background is an almost perfect blackbody, but slight distortions reveal events in the early cosmos. If primordial black holes were abundant and efficient at accreting, they would have injected energy into the plasma. Early analyses suggested tight constraints, but more recent work shows that accretion flows may have been radiatively inefficient, leading to milder limits. The uncertainties in accretion physics mean that constraints from spectral distortions remain subject to debate. Accretion is not the only way light can betray the presence of these objects. As tiny black holes evaporate, they emit radiation across the electromagnetic spectrum. The integrated effect of many such black holes contributes to the extragalactic gamma-ray background. This background provides an upper limit on how many small primordial black holes can exist. During certain cosmic epochs, primordial black holes might have grown by accreting dark matter or gas. Such growth could have left imprints on the distribution of matter or the ionization history of the universe, Observations of hydrogen's 21 centimeter line, which traces neutral gas, could reveal such imprints. Radio telescopes of the future may test these possibilities, adding another piece to the puzzle. While electromagnetic observations offer glimpses, gravity speaks in a language of its own. When two black holes spiral toward each other and merge, they release energy as gravitational waves, ripples in the fabric of spacetime. The detectors at LYGO and Virgo are sensitive to such waves. Several years ago, these observatories detected mergers of black holes with masses around 30 solar masses, prompting speculation that they might be primordial. Primordial black hole binaries can form in the early universe when density fluctuations lead to gravitationally bound pairs. Their merger rate depends on the abundance of the black holes and their spatial distribution. Too many would lead to too many mergers, in conflict with the observed rate. Thus, gravitational wave detections and non-detections set upper bounds on the primordial black hole fraction. The absence of a stochastic gravitational wave background is particularly constraining. If many primordial black hole binaries existed, their mergers over cosmic history would create a background of overlapping waves. LIGO and Virgo have not detected such a background, which implies strong limits on black holes in the mass range between roughly half a solar mass and 16 solar masses. This constraint sits beside those from lensing and dynamics, narrowing the window further. Another hallmark of primordial origins would be the existence of subsolar mass black holes. Standard stellar evolution cannot produce black holes lighter than about 2 solar masses. Therefore, detection of a merger involving objects with lower masses would point strongly to a primordial source. Searches for such events have been conducted, including those allowing for orbital eccentricities up to about 0.3, but no convincing candidates have yet been found. Eccentricity itself is another clue. Black hole binaries formed by dynamic captures in dense environments often have significant eccentricities when they enter the detector band. In contrast, primordial binaries formed in the early universe are expected to be nearly circular today. Observations of eccentric orbits could thus help distinguish formation channels. A lack of eccentric mergers in current data narrows down the possible population of primordial black holes. The gravitational wave frontier will expand as detectors increase in sensitivity and new observatories come online. Future facilities like the Einstein telescope and Cosmic Explorer will hear fainter signals and cover a broader frequency range. Space-based detectors like LISA will probe the merger of massive black holes at lower frequencies. Collectively, these instruments could reveal mergers from the earliest epochs and test the primordial hypothesis with unprecedented precision. Not all signals are continuous or periodic. Some arrive as singular transients, brief flashes across the electromagnetic spectrum. Fast radio bursts, millisecond-long radio flashes from distant galaxies, are among the most mysterious. Their origin is still uncertain, but their brevity and brightness make them ideal probes for gravitational lensing. If a compact object lies between us and the source, the burst could be split into 2 images, separated by a time delay comparable to the burst itself. Astronomers have begun searching for such lensed fast radio bursts in large catalogues. One analysis of hundreds of bursts from the CHIME telescope looked for pairs of pulses with identical spectra and a fixed delay. They found at most one candidate, suggesting that if primordial black holes with masses around 10 solar masses exist, they are rare. Future surveys with higher time resolution and more bursts will enhance this technique, allowing us to stack repeated bursts and improve sensitivity. Fast radio burst lensing is attractive because the optical depth to lensing grows with the distance to the source and the density of lenses. Also, the effect depends purely on geometry and mass, not on the internal physics of the lens. For a given population of primordial black holes, we can predict how often such lensing should occur. The current lack of lensed bursts thus places limits on the abundance of black holes in the mass range to which this technique is sensitive. Other transients may also bear the imprint of gravitational lensing. Caustic crossings occur when a source crosses the critical curve of a lensing system, producing sharp spikes in brightness. In stellar microlensing, this phenomenon can reveal planetary companions or small black holes. Observing caustic crossings in events with unexpected timescales could hint at exotic lenses. However, such observations require intensive monitoring and careful analysis. In the realm of gamma rays, short bursts can also be lensed by intermediate mass objects. The phenomenon of femtolensing we discussed earlier produces interference patterns rather than time delays, but at slightly larger masses, a short gamma-ray burst might be split into two pulses separated by microseconds. Detecting such features demands instruments with exceptional temporal resolution. New missions are being designed with this capability in mind. Transient lensing signatures have the advantage of being relatively free from background contamination. Because they rely on timing rather than absolute brightness, astrophysical uncertainties in the source play a smaller role. The challenge lies in collecting enough events to build a statistically meaningful sample. As global networks of telescopes expand and data sharing improves, the prospects for such searches will improve dramatically. The search for primordial black holes cannot rely on a single messenger. Each type of signal, photons, neutrinos, cosmic rays, gravitational waves, carries its own strengths and limitations. Some signals are susceptible to astrophysical backgrounds, while others depend on assumptions about the environment of the black hole. By combining these diverse probes, scientists hope to build a coherent picture of the hidden population of compact objects. This multi-messenger approach is akin to cartography. No single measurement can map the entire terrain, but multiple overlapping surveys can build a detailed chart. Gamma-ray observations set limits on low-mass evaporating black holes. Microlensing surveys constrain intermediate masses, and gravitational waves probe the heavy end. Dynamical heating fills in the gaps by limiting how many massive objects can wander in stellar systems. To make the most of this strategy, collaborations across disciplines are essential. Particle physicists work alongside astronomers and gravitational wave scientists. Data from neutrino observatories are cross-correlated with gamma-ray detectors to look for coincident bursts. Microlensing events observed in the optical are checked against radio and X-ray catalogues for any additional signatures. Each dataset is a thread woven into a complex tapestry. Advances in computing and machine learning have accelerated the search. Algorithms trained on simulated black hole signals can sift through vast amounts of data to identify subtle patterns. In microlensing, real-time analysis enables rapid follow-up observations of candidate events. For gravitational waves, machine learning helps distinguish true signals from noise and extract parameters such as mass and spin. The interplay between theory and data analysis is central to this field. As observational limits tighten, theoretical work explores new scenarios and refines existing models. For example, some theories propose that primordial black holes might cluster, altering their lensing and merger rates. Others consider non-standard accretion models that would change the expected electromagnetic signatures. By exploring the parameter space, theorists identify where current observations are sensitive and where new physics might hide. The story of primordial black holes is intertwined with the broader quest to understand dark matter. while many particles have been proposed as dark matter candidates. The possibility that some fraction resides in ancient black holes persists. These objects would be unique relics of conditions in the early universe, carrying information about processes that cannot be probed in any other way. Finding them, or definitively ruling them out, is therefore a high priority for cosmology. Future observatories promise to push the boundaries of our detection capabilities. The Vera Rubin Observatory's legacy, survey of space and time, will monitor the entire southern sky repeatedly, enabling detection of transient microlensing events and wide binary disruptions. The Square Kilometre Array will collect an unprecedented number of fast radio bursts, vastly increasing the chance of finding lensed pairs. Next-generation gamma-ray instruments will extend sensitivity to both lower and higher energies. Each new facility brings us closer to the critical sensitivity required to detect or exclude primordial black holes across all relevant mass scales. Space missions will also play a vital role. Satellites can observe the sky without interference from Earth's atmosphere, improving energy and time resolution. Future neutrino detectors in space or deep underground could capture the faint whispers of Hawking evaporation. Space-based gravitational wave observatories will open a new frequency band, potentially catching mergers of primordial black holes beyond the reach of ground-based detectors. The expansion of observational platforms marks a new era of discovery. Public interest in these searches underscores the universal appeal of cosmic mysteries. The idea that black holes could be as old as the universe itself touches on themes of origin and destiny. Artists, writers, and filmmakers have drawn inspiration from the notion of hidden objects shaping the cosmos. The scientific quest to detect them is a reminder that our understanding of the universe remains incomplete and open to surprises. In teaching and outreach, primordial black holes provide a gateway to topics such as general relativity, quantum mechanics, and cosmology. Explaining the concept of Hawking radiation introduces the merging of gravity with quantum theory. Lensing effects illustrate the curvature of spacetime. Discussions about dark matter lead to questions about the composition of the universe and the limits of our knowledge. In this sense, the search for primordial black holes is not just about detection, it is also about education and inspiration. Some theories speculate that small black holes might be abundant in the early universe, but decay before leaving any observable trace today. These transitory objects would still have influenced cosmic evolution through their radiation and interactions. Their existence could address puzzles in cosmology, such as the origin of baryon asymmetry or the nature of inflation. While speculative, such ideas drive researchers to look for indirect effects and to broaden the scope of inquiry. At the opposite end of the mass spectrum, extremely massive primordial black holes could have acted as seeds for supermassive black holes observed in galactic centers. These seeds would need to form very early to explain billion solar mass black holes seen at high redshift. If they existed, their growth through mergers and accretion would leave gravitational wave and electromagnetic signatures. Upcoming observations of quasars and gravitational wave backgrounds might shed light on this possibility. The interplay between astrophysical black holes and primordial ones adds complexity to the analysis. For example, the gamma-ray background includes contributions from active galactic nuclei and pulsars in addition to potential evaporating black holes. Gravitational wave data includes signals from stellar black holes, neutron star mergers, and possibly other exotic objects. Disentangling these contributions requires careful modeling and cross-checks. Sophisticated statistical techniques help isolate potential primordial signals from this cacophony. As new data accumulate, the constraints on primordial black holes become more precise. The non-detection of femtolensing patterns in gamma-ray bursts narrows the allowed mass window for low-mass black holes. Microlensing surveys continue to rule out large populations of Earth mass to solar mass lenses. Gravitational wave observations restrict possible populations of heavy black holes. Each limit is an invitation to look elsewhere and to refine search strategies. Collaborations between theorists and observers are essential to interpret these constraints. Theorists compute the expected signals for different black hole mass functions, spatial distributions, and formation histories. Observers design experiments and analyses to test these predictions. Feedback between theory and observation guides the allocation of resources and the development of new instruments. This iterative process is at the heart of scientific progress. In the course of this search, many innovative techniques have emerged. Some researchers propose using pulsar timing arrays to detect gravitational perturbations caused by passing primordial black holes. Others suggest examining the distribution of stellar velocities in dwarf galaxies for signs of heating. There are ideas to look for spectral lines from annihilation processes triggered by interactions near black holes. Creativity and ingenuity drive the exploration of every available avenue. As we picture these tiny gravitational ghosts moving through space, we may ask how they interact with dark matter itself. If dark matter consists of particles, these particles could be captured by or annihilate near primordial black holes, producing additional signals. Conversely, if dark matter includes both particles and black holes, interactions between the two components could alter the distribution of matter in galaxies. Such interactions are poorly understood, but may hold clues to the overall dark matter puzzle. Philosophically, the existence of primordial black holes challenges our notions of origin and creation. They would have formed not from collapsed stars, but from density fluctuations in the primordial plasma. Thus, they would be fossils from an epoch before stars and galaxies. Their potential to reveal conditions at that time makes them unique cosmic messengers. Studying them connects modern physics to the earliest moments of our universe. In constructing our narrative, we must maintain humility. The cosmos often surprises us, and many promising ideas have turned out to be false leads. Null results are not failures. They refine our understanding and guide the next steps. It is possible that primordial black holes contribute only a tiny fraction to the dark matter, or not at all. Even so, the journey of searching deepens our comprehension of gravity, quantum theory, and cosmology. Beyond the scientific implications, there is a poetic aspect to the search. The notion of ancient black holes quietly evaporating or lensing light from distant galaxies evokes images of cosmic ghosts. These ghosts may never reveal themselves directly, yet they influence the tapestry of the universe. Pursuing them requires patience, precision, and imagination. The very act of listening and looking sharpens our senses to the subtleties of nature. The synergy between observation and theory is an evolving story. As we gather more data and refine our models, the window on primordial black holes may either close or remain ajar. If the latter, we may one day announce a detection that changes our understanding of dark matter. If the former, we will have learned about many other astrophysical phenomena along the way. Either outcome enriches our knowledge. One cannot escape the parallel between this search and archaeology. Primordial black holes, if they exist, are fossils from the earliest times. Like archaeologists excavating ancient ruins, cosmologists sift through cosmic signals to uncover traces of these primordial entities. Each signal is like a shard of pottery or a fragment of bone, hinting at a larger story. The excitement lies in piecing together these fragments to reconstruct a forgotten era. Interdisciplinary collaboration extends beyond science. Artists have used the concept of primordial black holes to explore themes of memory, time, and oblivion. Musicians compose pieces inspired by gravitational waves. Writers craft narratives about invisible masses shaping destinies. These cultural expressions demonstrate how scientific ideas permeate broader human thought and provide fresh perspectives on our place in the cosmos. Education initiatives can leverage the allure of black holes to draw students into science. Hands-on activities illustrating gravity and space-time curvature bring abstract concepts to life. Simulations of lensing events show how mass distorts light. Discussions about Hawking radiation introduce the interplay between quantum mechanics and general relativity. These topics can foster curiosity and inspire future generations of scientists. The search for primordial black holes also has implications for new physics beyond the standard model. Some theories involve interactions between black holes and hypothetical particles, like axions or dark photons. These interactions could modify the signals we expect or produce entirely new phenomena. By combining gravitational and electromagnetic observations, researchers can test these ideas and potentially uncover new forces or symmetries. Recent advances in laboratory experiments may even offer analogues of Hawking radiation. Systems such as Bose-Einstein, condensates, and optical cavities can mimic horizon-like conditions. Observing analogous radiation in the lab helps build confidence in the theoretical framework. Such analogues, while not direct evidence of primordial black holes, contribute to our understanding of the underlying physics and support the broader search. The narrative of primordial black holes touches on the very beginning of time. Inflationary models predict fluctuations that, if amplified, could collapse into black holes. The distribution and masses of such black holes would reflect the shape of the primordial power spectrum. Thus, constraints on primordial black hole populations feed back into our understanding of inflation and the physics of the early universe. Each bound on black hole abundance constrains the amplitude of density fluctuations on scales otherwise inaccessible. Conversely, discovering a population of primordial black holes would have profound implications for inflationary theory. It would suggest that the power spectrum had features that caused enhanced collapse. This would guide theorists towards specific models of inflation or alternative early universe scenarios. The connection between microphysics at cosmic scales and astrophysical observations underscores the unity of physics across vast scales. The interplay between cosmology and fundamental physics extends to the dark sector. If primordial black holes comprise a fraction of dark matter, they coexist with other dark matter components. The relative contributions and interactions would influence structure formation. Observations of galaxy clustering, weak lensing, and cosmic microwave background anisotropies provide clues. Combining these cosmological probes with direct searches for black holes sharpens the picture. Throughout this exploration, the guiding principle is evidence. Theories can be elegant and appealing, but they must confront data. The search for primordial black holes is a testament to the scientific method. Hypotheses are tested against observations, and the results inform new hypotheses. This iterative process is open-ended, allowing for unexpected discoveries. The path may be long, but each step is meaningful. As observational techniques improve, we must also refine our statistical methods. Rare events require rigorous analysis to distinguish signal from noise. In gravitational wave astronomy, for example, distinguishing a subsolar mass signal from a noise fluctuation demands careful modeling of the instrument and environment. Similar challenges arise in gamma ray and neutrino astronomy. Robust statistical frameworks ensure that any claimed detection can withstand scrutiny. Meanwhile, attention must be paid to systematic uncertainties. In microlensing surveys, for instance, blending of stellar images can bias event timescales and magnitudes. In gravitational wave searches, uncertainties in waveform modeling affect parameter estimation. Recognizing and mitigating such uncertainties is crucial for drawing reliable conclusions. The success of multi-messenger astronomy depends on the integrity of each component. The global nature of these searches fosters international cooperation. Facilities span continents and oceans, with detectors in the Antarctic, underground mines, mountaintops, and space. Data are shared across borders and languages. This collaborative spirit reflects the universal nature of the questions being asked. The cosmos belongs to no single nation, but to all of humanity. In the near future, we might see dedicated missions to search for femtolensing and microlensing of gamma-ray bursts. Instruments with high time resolution and sensitivity could capture interference patterns or double peaks that escape current detectors. Large radio arrays might detect gravitationally lensed nanosecond transients. Each new capability opens a window onto mass ranges and distances previously inaccessible. Complementing observational efforts, there is a need for improved theoretical modeling of both black hole formation and backgrounds. Accurate predictions require understanding the distribution of density fluctuations in the early universe, the dynamics of binary formation, and the microphysics of Hawking radiation. Uncertainties in these models translate into uncertainties in interpreting the data. Reducing these uncertainties through theory and simulation is part of the path forward. Outreach and public engagement will play a role in sustaining support for these efforts, explaining why we search for objects we cannot see and how such searches advance knowledge, fosters appreciation for fundamental science. Engaging narratives, citizen science projects, and interactive visualizations can bridge the gap between complex physics and general understanding, empowering people to participate indirectly in the cosmic quest enriches the scientific enterprise. As we contemplate the end of our journey through this section of the story, it is important to remember that the universe is vast and full of hidden wonders. Primordial black holes, if they exist, represent one of those wonders. Their subtle signals challenge us to innovate and collaborate. By listening closely to the whispers of particles, photons, and space-time itself, we inch closer to uncovering secrets from the dawn of time. The search continues, and with it, the promise of deeper understanding. In the realm of quantum gravity, Hawking radiation stands as one of the few phenomena that marry quantum mechanics with general relativity. This radiation arises because quantum fields near the event horizon cannot remain in their vacuum state. Particle pairs form, and one particle falls into the black hole while the other escapes. The escaping particle carries energy away, causing the black hole to lose mass. As the mass decreases, the temperature rises, leading to a runaway process that culminates in a final burst. The theoretical spectrum of Hawking radiation is nearly thermal, but the presence of species of particles in the standard model modifies the details. At high temperatures, heavy particles become accessible and contribute to the emission. Detecting the full suite of particles would provide information about the particle content of the universe. In this sense, evaporating black holes could act as cosmic colliders. probing energies beyond those of human-made accelerators. When modeling the emission from a tiny black hole, physicists must consider both the blackbody spectrum and the grey-body factors that account for the barrier around the horizon. These factors depend on the spin of the particle and the curvature of space-time. Neutrinos have different transmission probabilities compared with photons and electrons. Calculating these probabilities accurately is essential for predicting the expected signal in detectors. The final explosion of a black hole with a mass of around 10 to the 15th grams would be extremely energetic, releasing on the order of 10 to the 30 joules in a fraction of a second. At a distance of a few light years, such a burst would saturate detectors. At galactic distances, the flux would be lower, but still detectable. Determining how frequently such events occur requires knowledge of the abundance of such black holes and their distribution in the galaxy. Some models predict that the final stages of evaporation may produce a unique burst of high-energy neutrinos. Unlike photons, neutrinos travel in straight lines, unaffected by magnetic fields. They could, therefore, provide precise directional information. An array of neutrino detectors scattered across the globe could triangulate the source of a burst and estimate its distance. Antimatter detection also requires careful analysis. The cosmic ray spectrum is influenced by the magnetic field of the galaxy, solar activity, and interactions with interstellar gas. To extract a possible signal from evaporating black holes, scientists must model these effects accurately. For instance, the antiproton flux measured by AMS-02 has been used to set limits on the abundance of low-mass primordial black holes. In addition to direct detection, models of nucleosynthesis can constrain the number of primordial black holes. If significant energy were injected during nucleosynthesis, the abundances of light elements like helium and deuterium would shift. Observations of these abundances agree with predictions from bigbang nucleosynthesis, limiting the amount of energy that could have been injected by black hole evaporation. This forms an indirect but powerful constraint on the population. Femtolensing, though currently yielding null results, remains a fertile area for innovation. Instrument sensitivity is limited by photon count statistics and the intrinsic variability of gamma-ray bursts. Scientists are exploring ways to combine data from multiple bursts to enhance sensitivity. Cross-correlating bursts with similar properties may reveal subtle patterns that would otherwise be lost. Microlensing has a rich history that predates the search for primordial black holes. Early surveys aimed to detect massive compact halo objects, MACHOS, as candidates for dark matter. While the original MACHO hypothesis has fallen out of favour, the techniques developed continue to be refined and applied to the PBH question. Each survey improves our understanding of the lensing rate and mass distribution in the galaxy. The shape of a microlensing light curve depends on the relative motion of the lens and source, the lens mass, and the alignment precision. For a given mass, the duration of the event scales with the square root of the mass. This means that higher mass lenses produce longer events. Short duration events could hide a population of low mass lenses if they occur often enough to overlap. Millilensing is sensitive to intermediate mass scales that are difficult to probe by other means. For example, a black hole of 10 to the 6th solar masses could lens a quasar jet, causing a knot in the jet to appear duplicated or magnified. Observing such effects requires high-resolution radio observations. Upcoming very long baseline interferometry arrays will provide the resolution needed to detect millilensing signatures. Beyond simple light curves, microlensing can reveal parallax effects. If a lensing event is observed from two different locations, such as Earth and a satellite, the light curves will differ slightly. This difference allows the determination of the lens distance and mass. Missions like Spitzer and Gaia have enabled parallax measurements that refine constraints on lens properties and improve the discrimination between primordial black holes and planetary lenses. The dynamical footprints of primordial black holes depend on the interplay between mass and number. A small number of very heavy black holes can have the same gravitational influence as a large number of lighter ones. Models of globular clusters often include dark matter components, and these can be compared with observations to set limits. The absence of excessive heating in such clusters speaks against a dominant population of heavy primordial black holes. Wide binaries are fragile because their gravitational binding energy is low. An encounter with a passing compact object can alter their orbits or break them apart entirely. Surveys that catalogue wide binaries and measure their orbital properties find that such systems are more abundant than would be expected if heavy black holes were common. This observation strengthens the constraints derived from cluster dynamics. Galactic disks are also sensitive to the cumulative effects of passing masses. Simulations show that repeated passages of black holes through a disk transfer energy to the stars, increasing their vertical motion. The resulting thickening would be observable as a change in the distribution of stellar heights above the disk plane. Because many spiral galaxies have thin disks, we can infer that heavy primordial black holes are not abundant. The combined dynamical constraints challenge models in which a significant fraction of dark matter consists of black holes, with masses above about 100 solar masses. However, these constraints often assume a uniform distribution of black holes. If the black holes were strongly clustered, their dynamical impacts might be confined to certain regions. This possibility is an active area of research, exploring whether clustering could relax some limits. Accretion physics introduces additional layers of complexity. The rate at which a black hole accretes depends on the density of surrounding material and the relative velocity between the black hole and the gas. In the early universe, the density was higher, but so were the relative velocities. Models of Bondi-Hoyle accretion show that under certain conditions, the accretion rate is suppressed, reducing the expected radiation. Different modes of accretion lead to different observational signatures. Spherical accretion is relatively inefficient at radiating energy, while disk accretion can be much more luminous. Disk formation requires angular momentum, which may be limited in the early universe. These considerations influence the constraints drawn from the cosmic microwave background and 21-centimeter observations. Spectral distortions in the cosmic microwave background are quantified by parameters that describe departures from a perfect blackbody. A positive chemical potential, for example, would indicate energy injection at specific epochs. Primordial black holes could contribute to such distortions if they release enough energy through accretion or evaporation. Upcoming experiments like PIXI aim to detect distortions at levels an order of magnitude below current limits. At redshifts around 20, neutral hydrogen interacts with the cosmic radiation field. The 21-centimeter hyperfine transition provides a tool for mapping the temperature and ionization state of the gas. If primordial black holes heated the gas, the 21-centimeter signal would be altered. Observations with arrays like HERA and SKA aim to measure this signal and constrain heating sources, including black holes. The gravitational wave story is still in its early chapters. Since the first detection, dozens of mergers have been observed. The masses and spins of these black holes span a range, with some lying in the so-called pair instability gap, where stellar evolution would not predict them. These anomalies revive interest in primordial explanations, though astrophysical channels may still account for them. The formation of primordial black hole binaries in the early universe involves the collapse of density fluctuations, followed by gravitational interactions with neighboring black holes and radiation. The cross-section for binary formation depends on the relative velocities and densities. Subsequent interactions with other black holes can perturb the orbits and lead to mergers. Numerical simulations attempt to model these processes to predict the expected merger rate. Another channel for binary formation occurs in later cosmic times, when black holes in halos sink toward the center through dynamical friction. In dense environments, like nuclear star clusters, capture events between black holes can form binaries that later merge. Such binaries often retain some eccentricity when they enter the LIGO/Virgo frequency band. Measuring the eccentricity distribution informs us about the relative contributions of early and late formation channels. Gravitational wave signals carry information not just about masses, but also about spins. If primordial black holes formed from collapse of primordial perturbations, their spins are expected to be small because the collapse would not impart large angular momentum. In contrast, black holes formed from stellar collapse or binary evolution can acquire significant spins. Extracting spin distributions from gravitational wave data thus provides another discriminator between astrophysical and primordial origins. The stochastic background produced by unresolved mergers is a key probe. As detectors improve, they will either detect this background or push the upper limit down. The amplitude of the background depends on the merger rate integrated over cosmic history and the typical energy emitted per merger. If the background remains undetected despite increased sensitivity, the allowed fraction of dark matter in primordial black holes will shrink. In addition to mergers of black holes, cosmic strings and phase transitions in the early universe can produce gravitational waves. Disentangling these contributions requires careful modeling and multi-band observations. Correlations with other messengers, such as gamma rays from cosmic string cusps or neutrinos from phase transitions, can help identify the source of a given background. This interplay exemplifies the power of multi-messenger astronomy. The gravitational wave memory effect is another phenomenon that may provide information. When gravitational waves pass, they leave a permanent displacement in the detectors. Measuring this displacement requires precise timing over long periods. Pulsar timing arrays are sensitive to this effect and could detect memory from supermassive black hole mergers or possibly from primordial events. Such measurements would complement those from laser interferometers. Fast radio bursts themselves remain a mystery. Some originate from magnetars, but others lack clear associations. The question of whether all FRBS originate from the same class of objects or multiple progenitors remains unresolved. Lensing studies rely on having a large sample of bursts with well-understood properties. As we learn more about FRBS, the constraints on primordial black holes derived from them will become more reliable. Time delay echoes, whether in radio, optical, or gravitational waves, require precise synchronization of instruments. In radio astronomy, cross-correlating signals from multiple telescopes can improve timing accuracy and sensitivity to lensing. For gravitational waves, networks of interferometers around the world provide redundancy and improved localization. Coordinated observations across different messengers enhance the robustness of any claimed lensing event. The phenomenon of caustic crossings illustrates the complexity of gravitational lensing. As a source moves across the lensing caustic, the magnification can change dramatically. Monitoring campaigns in the optical band have caught such events and used them to measure the properties of the lens. Extending these techniques to search for primordial black holes will require patience and persistence, but the potential payoff is significant. In some scenarios, lensing by primordial black holes could also modulate the timing of repeating signals. For example, if a pulsar signal passes near a black hole, the arrival times of pulses could show a distinctive pattern. Pulsar timing arrays monitor millisecond pulsars with incredible precision. Any anomalies in arrival times could hint at transient lensing. This method offers another way to probe intermediate mass lenses. Ultimately, the most compelling evidence will come from converging lines of inquiry. A detection of a neutrino burst, coincident with a gamma-ray flare of the right spectrum, coupled with a gravitational wave or microlensing signal, would be persuasive. Even short of such a coincidence, consistent hints across multiple channels can build a cumulative case. Conversely, the absence of signals across all channels strengthens the case against a significant primordial black hole population. The principle of statistical ensemble applies here. Rare events may occur by chance, but multiple independent occurrences are unlikely to be coincidental. Thus, the accumulation of weak hints across datasets can lead to a strong inference. This strategy is already employed in high-energy physics and cosmology. Adapting it to the search for primordial black holes is a natural progression. Modern astronomy generates enormous amounts of data, far beyond what human analysts can inspect manually. Machine learning algorithms, trained on simulated lensing events, gravitational waveforms, and particle cascades, can scan through terabytes of observations. These algorithms must be carefully validated to avoid biases and false positives. Open datasets and cross-validation among different teams help ensure reliability and foster innovation. Citizen science projects also contribute. Platforms like Zooniverse allow volunteers to examine microlensing light curves or classify transient events. Non-expert participation not only accelerates data processing, but also engages the public in scientific discovery. Projects focusing on gravitational lensing have yielded discoveries of new lensing systems. Similar initiatives could be extended to primordial black hole searches. As we think about the far future, we might imagine a universe where we have mapped out all astrophysical sources and backgrounds. In such a scenario, any unexplained signal would stand out clearly, making the search for exotic objects easier. Achieving this requires persistent cataloging and monitoring of the sky across all wavelengths and messengers. The goal is ambitious, but not out of reach with continued technological advancement. The search for primordial black holes intersects with the study of compact object mergers in dense star clusters. Dense clusters can undergo core collapse, leading to runaway growth of black holes through successive mergers. The resulting heavy black holes could themselves be lensing sources. Differentiating these astrophysical black holes from primordial ones requires understanding the formation history of clusters and their environments. Furthermore, the metallicity of the progenitor stars influences the mass spectrum of black holes formed through stellar evolution. Low metallicity stars lose less mass through winds, resulting in heavier black holes. Observations of black hole masses can thus constrain the metallicity distribution of early star formation. This, in turn, affects the interpretation of gravitational wave data in terms of primordial or astrophysical origin. In another vein, primordial black holes might have acted as seeds for structure formation. Even a small fraction of dark matter in compact objects can enhance the collapse of gas clouds. This could lead to earlier formation of stars and galaxies. If true, primordial black holes would indirectly influence ionization and the timeline of cosmic history. Observational signatures of early star formation could therefore provide indirect evidence for or against their presence. The interplay between small-scale physics and large-scale structure is a fascinating aspect of cosmology. Tiny fluctuations in the early universe can grow into galaxies, and similarly, tiny black holes can influence large-scale phenomena. Tracking these influences requires combining observations of the cosmic microwave background, large-scale structure surveys, and local astrophysical measurements. Coordinated analysis across these scales is a formidable challenge, but promises rich rewards. Occasionally, theories propose that primordial black holes could account for anomalies in other measurements. For instance, hints of excess gravitational lensing in some galaxy clusters or unusual microstructure in quasar flux ratios might be attributed to unseen lenses. While these anomalies often have conventional explanations, keeping an open mind allows for the possibility of discovering new physics. A careful balance between skepticism and openness is essential in scientific inquiry. The cross-disciplinary nature of primordial black hole research fosters innovation. Techniques from statistical mechanics, data science, numerical relativity, and plasma physics all play roles. Students entering the field find opportunities to learn a wide range of skills. This diversity enriches the scientific community and ensures that the field remains dynamic and creative. As we look back over the decades of research, we see that the primordial black hole hypothesis has evolved. Initially proposed as a curiosity, it has become a serious contender in the dark matter debate. Advances in instrumentation, theory, and data analysis have steadily improved our ability to test the hypothesis. The question remains open, but the progress made speaks to the strength of the scientific enterprise. Even if primordial black holes turn out to be a minor component of dark matter, the techniques developed to search for them will have lasting value. They will continue to be applied to study exoplanets, stellar remnants, and other compact objects. The cross-fertilization between different subfields of astrophysics accelerates discovery. In this sense, the search itself is as valuable as the potential discovery. Finally, the journey of exploring the universe invites reflection on our place within it. The idea that the universe contains relics from its birth reminds us that we are part of a much larger story. Our curiosity drives us to seek connections between the smallest scales and the largest. Whether or not primordial black holes exist, the endeavor to find them enriches our collective understanding. It teaches us patience, perseverance, and the joy of discovery. While the narrative has flowed through many channels, another subtle messenger remains to be highlighted. Neutrinos, nearly massless and weakly interacting, can traverse dense environments that stop photons or charged particles. Detecting neutrinos from evaporating primordial black holes would complement gamma-ray observations and could break degeneracies in emission models. Neutrino observatories operate almost continuously with minimal downtime, making them invaluable partners in multi-messenger campaigns. Coordinated analysis of neutrino, photon, and gravitational wave data may uncover correlations that elude single-channel studies. Cosmic rays offer another complementary perspective. Evaporating primordial black holes could accelerate antiprotons and positrons, adding to the high-energy cosmic ray background. By modeling the propagation of these charged particles through galactic magnetic fields and comparing with observations, researchers can constrain the abundance of such black holes. Combining cosmic ray data with neutrino observations refines estimates of the energy budget and helps disentangle contributions from astrophysical sources. As instruments improve, the accessible parameter space for these constraints will continue to expand. Looking ahead, the prospect of detecting simultaneous flares across neutrino, gamma ray, and gravitational wave observatories is particularly exciting. Such coincidences could signal the final moments of a primordial black hole, or the merger of a compact binary. Observatories are developing rapid alert systems to respond to these events, enabling quick follow-up across the electromagnetic spectrum. Integrating diverse datasets requires careful calibration and sophisticated statistical methods, but the potential rewards are immense. This synergy exemplifies the collaborative spirit driving the search for primordial black holes and underscores that the story is still unfolding.